Sir, can we start the program, sir?
Yes, we can start.
Okay. Nivedita, ready?
Yes, sir.
Please start.
Okay, sir. A very warm good evening to everyone. Louis Pasteur once said, "Science knows no country because knowledge belongs to humanity and is the torch which illuminates the world." With this note, I welcome our most honorable chief guest, Professor Dr. V. Tyagarajan, who has kindly consented to be the speaker of today to grace this session. I also welcome Professor Dr. S. Kuttirani, Dean, School of Physical and Chemical Sciences, Professor Dr. D. Ishwaramurthy, Head of the Department of Chemistry, Professor Dr. N. Vasimalai, Coordinator, faculty members, and participants. I welcome you all to the very successful 16-day streak of one-month summer internship program on recent advances in chemical sciences. It's my privilege to give the chief guest introduction about our most respectable chief guest, Professor Dr. V. Tyagarajan. Professor Dr. V. Tyagarajan is currently working as an UGC Assistant Professor, School of Chemistry, Bharathidasan University, Trichy. He had received his PhD from University of Madras as a junior and senior research fellow. He had his postdoctoral research at various prestigious international institutions, including Tohoku University, Japan, from 2005 to 2008, Atomic Energy Commission, France, from 2008 to 2010, École Normale Supérieure, France, from 2010 to 2012, and also at International Iberian Nanotechnology Laboratory, Portugal, from 2012 to 2013. Since 2014, he has been working as an UGC assistant professor. His areas of research are photonics and biophotonics, ultrafast spectroscopy of biomolecules, photonic cancer therapy, nanomedicine, fluorescence sensors, and photobiology. So far, he had published 38 research articles in various highly reputed international journals. He had
ரைட் அப்
given
மாதிரி அந்த லைக் உள்ள என்னென்ன வேர்ட்ஸ் வேணும் அப்படின்னு.
Nivedita, please unmute your mic. Your voice is not audible.
Yes, sir. Now is it audible, sir?
Yeah, now it is audible. Yes, please.
Okay, sir. His areas of research are photonics and biophotonics, ultrafast spectroscopy of biomolecules, photonic cancer therapy, nanomedicine, fluorescence sensors, and photobiology. So far, he had published 38 research articles in various highly reputed international journals.
Nivedita, again you are in mute condition. Please check your mic. Unmute by yourself.
His index is 17, and he is guiding a several number of postgraduate student and PhD scholars. He is also in the highly prestigious DST Young Scientist Award in 2015. Khan once said, "Every thought you produce, anything you say, any action you do, it bears your signature." As like that, the research works of our chief guest have their unique signature, resembling his knowledge and his experience. With this note, I once again welcome our most eminent chief guest, Professor Dr. V. Tyagarajan. I heartily welcome you, sir. Now, I hand over the session to Professor Dr. V. Tyagarajan.
Good evening to one and all. Can you hear me?
Yes, sir, we are hearing you.
Okay. Good evening, one and all. First of all, I would like to thank Vedita for the nice introduction, and Wasimala and all the faculty members of this department for giving me this opportunity. This section, this presentation is only for students, so you can during any time, you can stop me and ask any questions, whether it's related to my presentation or if you have any basic doubts in spectroscopy or fluorescence spectroscopy or anything related to biomolecular spectroscopy, you can stop me and ask. If I know the answer, I will explain to you. With this small introduction, I will start my presentation in fluorescence spectroscopy. Is my screen visible?
Yes, sir, visible, sir.
Okay. The fluorescence spectroscopy, it's very popular nowadays because of its lot of advantages. Because in our body, we have more than 50,000 different kinds of proteins. Each and every proteins carry out different functions. In order to understand this function and the relationship between the structure and functions of these proteins, a lot of spectroscopy techniques are available. Among the techniques, the fluorescence spectroscopy is more advantageous because here we use the less radiation. We are going to use the UV and visible radiation, especially if we are related to the amino acids. We are going to use UV radiation. In the case of cofactors, if you use any cofactors on the proteins, if we want to excite, we are going to use visible light. So these lights are not that harmful like other X-ray or other radiations. So the proteins are very stable. We can keep the structure intact during our studies. So, and in addition to that, we have a lot of fluorescent probes nowadays available in order to understand the malignant tumors. We can exactly locate the tumors before the operations. In addition to the advantage is we can separate the malignant tumors from other normal cells very easily, and we can remove the tumor very easily. A lot of people are working on in that area also. Not only that, we can go in the single molecular level to understand the single enzyme or single protein functions using fluorescence spectroscopy. With this small introduction, I'm going to talk about the very basics of fluorescence spectroscopy because you are a student. But if you have any doubt in your research or if you have any clarification, also you can ask me in advanced level also. It doesn't matter anytime. Feel free to, because this section is only for you. If we talk about the fluorescence spectroscopy, we cannot talk about the fluorescence spectra without Jablonski diagram. Jablonski diagram is a very simple diagram to explain what's happening when we excite any molecule. All the molecules absorb the light. For example, if my black board is black because it absorbs all the radiations coming from the sunlight. If the umbrella is white or my wall is white, because it reflects all the sunlight coming from the all the light wavelengths coming from the sun. So the light absorption is very important phenomenon, because if I want to see any objects inside my room or outside, uh, we need a sunlight. Without sunlight, we cannot see any objects. So if we want to see any object, the object should interact with the light. The study of interaction of light with the matter is called photonics. If the light interacts with the biomolecules, it's biophotonics. If it interacts with any materials, it's called photonics. So all the molecules interact with the light one on another way. All molecules absorb the light. Whether it may be some molecules absorbs in the UV region, some molecule absorbs in the visible region, some molecule is absorbs in the infrared radiation. Only that's different. Other than that, all molecules absorb the light. In contrast to the absorption, only few molecules emit light. Once we shine the light or photons to the molecule, it goes from the lowest singlet excited state to higher singlet excited state. It may go to the S3 or S4 anywhere. These are the vibrational levels, different vibration level within the ground state, and this is the vibration level within the first singlet excited state S1. This is the second singlet excited state S2. When we excite the molecule, it goes to any excited state. Immediately after goes to the any excited state from the S2 or S3 or S4 or from Sn, it returns back to the ground state, lowest singlet excited state within femtosecond time scale. The femtosecond time scale means in the order of 10 to the power of minus 15 seconds. The flashlight coming from the camera is in the order of milliseconds. Then you can understand the duration of the femtoseconds. Not see it with our own eyes because it's very fast, very short duration. So within 10 to the power of minus 15 seconds from the higher excited state to the ground state, lowest singlet excited state, it returns back via internal conversion. Internal conversion is nothing but it gives the excess energy through heat. It's a non-radiative pathway to the surrounding or to the neighboring molecule and return back to the lowest singlet excited state S1. From S1, the molecule return back to the ground state in two different pathways. One through the non-radiative pathway called intersystem crossing. From the lowest singlet excited state. Pardon? From the lowest singlet excited state to lowest triplet excited state through non-radiative pathway. That also through heat. So from the it goes to the triplet or it returns back to the lowest ground state. That is the ground state through radiative pathway or non-radiative pathway. Non-radiative pathway is the internal conversion. Radiative pathway is a fluorescence. So whatever we are focusing on that, when we excite the molecule, it goes to the excited state. From the excited state, it returns back to the ground state via two different pathways through internal conversion or radiative pathway called fluorescence. We are focusing mainly on fluorescence, not on phosphorescence. If the molecule returns back from the triplet state to the lowest ground state, then it's called phosphorescence. So two non-radiative pathways. One is the internal conversion, another one is the intersystem crossing. Both are through heat. Non-radiative means it's heat. Two radiative pathways from the excited state. One is the fluorescence, another one is the phosphorescence. Fluorescence occurs from the lowest singlet excited state. Phosphorescence occurs from the lowest triplet excited state to the ground state. The phosphorescence, because its phosphorescence occurs from the triplet state to the singlet state, so the spin flip should occur. So normally the phosphorescence occurs in a very slow time scale, so in the order of microseconds to milliseconds or milliseconds to seconds, depending upon the molecule. The fluorescence is a very fast. It occurs in the order of 10 to the power of minus 12 to 10 to the power of minus 9 seconds. That is the picoseconds to nanoseconds. So fluorescence spectroscopy measuring the light given off by an electrically excited molecule. If we excite the molecule goes to the excited state. From the excited state, it gives return back to the ground state through emission of photons through radiative pathway. It's called fluorescence. When we shine a light from the highest occupied molecular orbital, the electron goes to the higher excited state. We excite one of the electron is excited to the excited state. From the excited state, it emits through radiative pathway and return back to the HOMO, the same ground state, through fluorescence. In another case, it goes to the triplet state. From the triplet state, it emits also. That also possible through intersystem crossing. It goes to the triplet state. You can see the triplet. The spin is the same. It's a two. We can call it a singlet, and triplet means it's a 2s plus 1. If the electron spins are opposite, so the s is equal to 0, 2s plus 1 is equal to 1. So it's a singlet. If the two electrons are in the same spin, then total s is equal to 1, 2s plus 1 is equal to 3. It's a triplet state. So the triplet state also it emits return back to the ground state by emitting the photons is called the phosphorescence. So we have two important processes when we excite the molecule. One is the fluorescence, another one is phosphorescence. If some molecule it doesn't emit fluorescence as well as phosphorescence, and it gives its excess energy through a non-radiative pathway as a heat. That also possible. That's the reason I mentioned in the beginning itself. All molecules absorb the light, only few molecules emit. Some molecules emits through fluorescence, some molecules emits through phosphorescence. Some of the molecule gives its excess energy to the solvent or surrounding or environment as heat, and return back to the ground state. So the singlets, the fluorescence occurs from the same spin state. Singlet excited state to the singlet ground state. It's a spin allowed transition because singlet to singlet, it's allowed transition. So it occurs very fast in the order of picoseconds to nanoseconds. And mostly it occurs in the organic molecules like ethylene, anthracene. We see a lot of molecules, fluorescing biomolecules, a lot of markers that TAPI. A lot of fluorophores are available in the literature. A lot of people are working on developing a new probes for biomolecules also. In the end, I will mention what are the important criteria or conditions needed for designing a probe for biomolecules also. In the case of triplet state, the triplet phosphorescence, the emission occurs from the triplet state to the ground state. So it's a spin forbidden transition because it's triplet to singlet. The electron should change its spin. It's not allowed transition, so it's very slow and it occurs in the order of microseconds to second. Mostly it occurs in transition metal complex. The well known is a ruthenium bipolar complex, ruthenium tris bipolar. That complex, the lifetime also very long, in the order of microseconds, and it's a very stable complex also. So from the Jablonski diagram, we can understand what's happening when we excite the molecule. When we excite the molecule goes to any excited state. This is the simplest Jablonski diagram. It's not the very complicated one. We remove all the vibrational levels. We kept only electronic tensions here, electronic energy levels here. So we have a S0, it's a ground state energy, and then S1 is the first singlet excited state, S2 is the second singlet excited state, T1 and T2 are first triplet and the second triplet. When we excite the molecule, it goes to the excited state, it goes to any higher excited state, maybe it goes to S2 or S3, S4, it depends on the energy we given to the molecule. And immediately it uses excess energy through internal conversion, return back to the lowest singlet excited state, S1. From S1, it returns back to the ground state through non-radiative pathway, internal conversion, through heat, or radiative pathway through fluorescence. Or intersystem crossing to the T1. From T1, it returns back to the ground state through non-radiative as well as the radiative pathway. Radiative pathway is phosphorescence. These are the simplest Jablonski diagram. If you have a quencher, the fluorescence quencher is nothing but a molecule which quenches the fluorescence. If you add the molecule to the fluorophore or solution of the fluorophore, it quenches its fluorescence. These molecules are called quencher. If you have a quencher, then it's the Jablonski diagram a little bit complicated. We don't worry about it. Normally, most of the people they deal with the organic molecule. If we deal with any organic molecule, it has three different kind of electrons: sigma electrons, pi electrons, and then non-pointing electrons. So in the organic molecule, we are going to deal with only these transition N to pi star, pi to pi star, mostly N to pi star and pi to pi star. In some cases, N to sigma star, sigma to pi star, sigma to sigma star. But most of the molecule we are going to deal with the N to pi star and pi to pi star transitions, because the energy level is very good. N to pi star is 1 meter and the pi to pi star is here. So these two electronic energy levels we are going to deal with other things. If we take the molecules like naphthalene or anthracene, in the molecules like naphthalene and anthracene, we don't have any non-bonding electrons. In this case, we have only pi. We are going to deal with the pi electrons. In this case, we are going to deal with only pi to pi star transition. So depending upon the molecules, we are going to deal with both N to pi star as well as pi to pi star transition. In some cases, we can see that N to sigma star, sigma to pi star, sigma to sigma star. In the case of inorganic molecules, we have a lot of transition like metal to ligand charge transfer, ligand to metal charge transfer, ligand transition, metal transition. All the transitions will be there, but we are not going to discuss about the inorganic complexes. We are mainly going to focus on the organic molecules. When the organic molecules, only two transitions are important: N to pi star and pi to pi star. So if we want to find out whether the molecule, the transition we observe is N to pi star, pi to pi star, a lot of methods are available. We can play with the solvent polarity, we can find it out, or from the energy level we can find it out. A lot of possibilities are there. So this is the Morse diagram. The same energy level I can represent as a Morse diagram. So within the electronic level, we have a different vibration level also. This is the ground state potential energy, and this is the first singlet excited state potential energy. When we excite the molecule, it goes to any higher energy level, vibration level, because it's a straight. When we excite it, excitation is very fast in the order of femtosecond, the 10 to the power of minus 15 seconds. During this electronic transition, no structural change occurs. Once when it goes to the higher vibration level of the first excited state, it returns back to the ground's lowest singlet excited state. That is the lowest vibration level through internal conversion. That is also very fast in the order of picoseconds. And in this case, some structural change occurs. If the molecule undergo any excited state reaction, during the excited state of the lifetime, some changes may occur. For example, if you are dealing with the excited state intramolecular proton transfer kind of molecules, the proton transfer occurs within the time scale also. or less than that, in the order of 10 to the power of minus 15 second or femtoseconds also it's occurred. The fluorescence, we are dealing with the fluorescence. Fluorescence is a very slow process compared to the internal conversion, is in the order of nanoseconds to picosecond. No structural change occurs during the fluorescence. It is the same. It's the relation between the internal conversion and fluorescence. The fluorescence is very slow compared to the internal conversion. Internal conversion is very fast. Another important rule when we deal with the electronic transition, electronic emission, it's a Kasa's rule. Kasa is a scientist who discovered the emission predominantly occurs from the lowest excited state. Whether it's maybe a triplet or singlet, it doesn't matter. If the emission occurs from the triplet, it's phosphorescence. If the emission occurs from the singlet, it's fluorescence. But in both cases, the emission occurs only from the lowest singlet excited. So lowest excited state, not from the T2 to S0, not from T3 to S0, not from S2 to S0, not from S3 to S0. It's always occurs from the S0 to S1 to S0 or T1 to T0. Sorry, it should be S1 here, not S0. So S1 to S0 or T1 to T0. It's a very important rule. The cause he discovered during the period of 1920 to 2013. He lived some very Casa's laboratory also there. It's a well-known laboratory. The emission predominantly occurs from the lowest excited state. In the case of fluorescence, it occurs from lowest singlet excited state. In the case of phosphorescence, it occurs from the lowest triplet excited state. The emission always occurs from the lowest singlet excited state. The energy of absorption is always higher than the energy of the emission energy. The absorption energy is always higher than the emission energy because some of the excess energy is given to the surroundings through internal conversion. So the energy E is equal to hν. E inversely proportional to the lambda wavelength. So once the energy is high, the wavelength is low. When the energy is low, the wavelength is higher. In the case of emission, it always occurs from the lower energy than the absorption. That's the reason when we see the absorption and emission spectra, the emission always occurs from the lowest lower energy than the absorption. If we discuss about it, the wavelength, it's always in the higher wavelength than the absorption. So the emission is redshifted relative to the absorption. Absorption is blue shifted relative to the emission. So, if we are talking about the energy scale, it's opposite. If we are talking in the wavelength scale, it's opposite. So vibration levels also, some cases, vibration levels also play a key role in the absorption and emission process. We can see some of the emission process, we can see that the emission occurs to the different vibration level also. From S1 to V is equal to 5, S1 to V is equal to 4, S1 to V is equal to 3. Some cases we can see these transition also within that, you can see these are the vibrational transitions. The shoulders are vibrational transition. This is the main peak, but in addition to that, we can see the different peaks also. This shoulder, small shoulder. The vibration levels in the excited state and the ground states are similar. The absorption spectrum reflects the vibration levels of the electronically excited state. The emission spectrum reflects the vibration level of the electronic ground state because it occurs from the lowest singlet excited state as well as the lowest vibration state of the singlet excited state. So it V is equal to 0 to ground state V is equal to 5, ground state V is equal to 4, ground state V is equal to 3 it occurs. So the emission spectrum reflects the vibration level of the electronic ground state, not the excited state. Fluorescent emission spectrum is the mirror image of the absorption. Most of the molecules The absorption spectrum is totally mirror image of the emission spectrum. The emission spectra is totally mirror image of the absorption spectra. You can see the different absorption. If you see it, this is the from the v is equal to 0 to v is equal to 5, v is equal to 0 to v is equal to 4, v is equal to 0 to v is equal to 3, like this. And the emission also is similar. V is equal to 0 to v is equal to 0, v is equal to 0 to v is equal to 1, v is equal to 0 to v is equal to 2, v is equal to 0 to v is equal to 2. So we can see that the vibrational pattern also within the emission molecules. But these vibrational patterns, it depends on the environment, it depends on the solvent, it depends on the surrounding. Depending upon the solvent and the surrounding, these vibrational patterns also change. So in the mirror image relationship, you can see the well-known molecule fluorescein. Fluorescein is a well-known biotag. People tag the biomolecule with the fluorescein, happy this kind of molecule because the quantum yield is very high and it's highly fluorescent, and in addition to that, it's very stable. When we design any fluorescent probes, these are the main kind of criteria. It should soluble in water and it should have high quantum yield, and the stability should be very high. The thermal stability as well as the photostability. So it should be stable at a different temperature also. At the same time, it's stable when we shine a light. It should be stable for a longer period also. These are the main criteria when we design a fluorescent probe. So etherium bromide, any people working in biology, they will know because for a DNA binding, those kind of studies, the people use etherium bromide. When we run the cell, if we run the PCR polymerase chain reaction to amplify the DNA, after amplification, in order to find out whether the DNA is amplified properly or not, we run the gel and then use the etherium bromide stain in order to find out whether we have the bands at the exact position. The PCR went very well, the primer acts very well or not. Those kind of information we can get it from etherium bromide. Anthracene, you can see it in anthracene and pyrene, these kind of molecules, the pi star kind of molecule, you can see the vibrational patterns very clearly, both in the absorption as well as the emission spectra. And you can see the fluorescence spectra always redshifted compared to the absorbance. Another important, when we're dealing with any fluorescent probes, the important thing is the Stokes shift. The Stokes shift is the wavelength difference or energy difference between the absorption and the emission maximum. So we know the absorption maximum of this peak and we know the emission maximum of this peak. We can convert it. This is a wavelength always in nanometer. We can convert it into wave number also, or we can convert it into energy kilocalories also. We can take the difference between these two peaks. We will get the Stokes shift. Why the Stokes shift is very, very important. Whatever the molecules, whatever the probe molecules available in our body, all absorbs in the UV and visible range. All the cofactors, everything. If the Stokes shift is very high, the emission coming from the probe, it doesn't interfere with the probe molecules already available in our body, like cofactor, flavin, tyrosine, tryptophan, phenylalanine, this kind of amino acids. It doesn't interfere. So we can see the fluorescence only from the probe. That's the reason always bio people always look for a fluorescent probe which shows the large Stokes shift. Stokes shift means the absorption emission should separate far away. It's not in the very close line. It's far away from each other. And the Stokes shift, it depends on the solvent polarity and the temperature and the hydrogen bond. For example, if we have a donor and acceptor, if I use the methanol or water, the methanol and water, the solvent hydrogen bonding interaction with the probe and it changes its Stokes shift also. The temperature also play, because temperature play with the rigidity of the molecule. It changes the rigidity of the molecule, then it changes the Stokes shift also. Solvent polarity, if the charge transfer occurs, we have the normally charge transfer occurs if the molecule contains the donor and acceptor If the charge transfer occurs, the electron shifts from the donor to the acceptor in the excited state. So the donor is del positive in the excited state here, and acceptor is a del negative in the excited state. So if I use the more polar solvent, it will stabilize the charge transfer. So stabilization means lower energy means higher wavelength. So we will have a more rich. For example, if I use a DMSO, if I dissolve the probe, very polar probe in toluene and DMSO is more polar solvent, and toluene is a less polar solvent, and both are aprotic solvent. So aprotic means it doesn't have any hydrogens. So these two solvents, when we dissolve it and measure it, the DMSO stabilizes the charge transfer better than the toluenes. So the toluene, we can see the emission in the blue region, and the DMSO, we can see the emission in the red region. We can see the very well-known probe, DNS, 4-dimethylamino 4-nitrostilbene. This is a well-known probe because this probe shifts with the solvent polarity enormous. You can see it. It's from 400 to 800, almost to 400 nanometer short shift region. And depending upon the solvent, we can tune the emission of the probe. We can have it blue, we can have it green, we can have it yellow, we can have it red from the same probe. Because we can tune, we can stabilize the charge transfer in a different pattern. You see it here. We have a donor, we have the acceptor. So the charge transfer occurs from donor to the acceptor. When we use a more polar solvent, it stabilizes the charge transfer and the emission occurs at the higher wavelength. So this is the case. So you see the hexane, it's in the blue, and then N-butanol, you see it in the red. This way we can play with the solvents and we can tune the polarity of the solvent, emission wavelength of the probe. What is the advantage of these kind of probes? These kind of probes can bind the different locations and gives a different fluorescence. Same probe can able to detect different organelles in the same cell, like mitochondria. Lot of organs we can detect. The another important property is the solvatochromism. For example, if I excite these DNS, the DNS goes to the excited state, then the dipole moment of this molecule in the ground state is totally different. The excited state is totally different from the ground state because different kind of charge distribution occurs in the excited state, because in the excited state the donor is del positive and the acceptor is del negative. So the solvent molecules reorient around this donor and acceptor and stabilize or destabilize this charge transfer state, results in a different emission field. So the solvatochromism, solvent also play a key role. A lot of people working on solvation dynamics also. How long does it take to the solvent stabilize the city state, or how long does it take to reorient the solvent around the excited state? This kind of things, occurs within the lifetime of the molecule. The lifetime is nothing but the average time of the molecule stays in the excited state. When you excite the molecule, it goes to the excited state. How long does it stay in the excited state? Within the time period, the solvents reorient. The solvation dynamics is in the order of femtoseconds or picoseconds. Femtosecond to picoseconds is faster than the emission. The characteristics for any probes, these four characteristics are very important. Energy is directly inversely proportional to the wavelength, whether it's emit in the blue or green or red. The wavelength is very important when we design any probe. And the lifetime, as I mentioned earlier, it's the average time of the molecule stays in the excited state. When you excite the molecule goes to the excited state and it stays in the excited state. So just we are going to find it out, how long does it stay in the excited state before returning back to the ground state. This average time of the molecule stays in the excited state, it's called fluorescence lifetime. If you measure the lifetime of the fluorescence, then it's called fluorescence lifetime. If you measure the lifetime of the phosphorescence, is called phosphorescence lifetime. But in the common, lifetime is nothing but the average time of the molecule stays in the excited state. The another important criteria for any probe is the quantum yield. Quantum yield is the number of photons emitted divided by number of photons observed. So always number of photons emitted by the molecule is always less than the number of photons observed by the molecules. So the quantum will be always less than 1 for any molecules. And then the important criteria is polarization. Polarization is very not important for organic molecule. Polarization is important for biomolecules. If the biomolecule is bigger, during the exhalation, the molecules is in a different orientation. After at the time of emission, the molecules reorient themselves. So the polarization is different. From this, we can get a lot of information. From the by measuring the anisotropy, we can get a lot of information from that also. So the quantum yield is the important criteria. When we design any probe, first the people measure the quantum yield. The quantum yield is the number of photons emitted divided by the number of photons absorbed by the molecule. So number of photons emitted means for in the case of fluorescence, number of photons emitted from the singlet excited state divided by the number of photons absorbed. So photons emitted is the radiative. As I mentioned, the emission is always the fluorescence of phosphorus, the radiative decay constant, and the non-radiative. Non-radiative means internal combustion intersystem crossing. So this K is total radiative as well as non-radiative decay constant. K is equal to radiative plus non-radiative. This is the radiative decay constant. Kr divided by Kr plus Knr. That's the K they mentioned here. 1 by Kr plus K, radiative plus Knr, radiative plus non-radiative decay rate constant equal to lifetime of the above. So this is the way also they can measure it. If we know the lifetime and if we know the quantum yield, from that we can calculate the radiative rate constant as well as the non-radiative decay constant of any of the molecules. The quantum yield, it depends not only on internal conversion and intersystem crossing, it depends on the solvent, whether it's a solvent acts as a quencher or not. If we have two different probes, if we have a biomolecules inside it, then we have a FRET also. The FRET is another important phenomena when we deal with biomolecules, fluorescence, resonance, energy transfer. Fluorescence, resonance, and energy transfer, when we have two probes inside the solution, the emission spectrum of the one probe overlap with the absorption spectrum of another probe. The energy transfer occurs in the excited state. So we cannot see the emission from the excited molecule. We can see the emission from the another molecule which absorbs the emission of the light from the excited molecule. So we can see the more red wavelength. So this fluorescence, resonance, energy transfer, it depends on the distance between the donor and acceptor, R power 6. So the distance is inversely proportional to the R power 6. So it's when the distance decreases, the rate of energy transfer also very high. When the distance is further, the rate of energy transfer also very low. So it's R power 6 increases, R power 6 decreases. So it depends on the distance as well as the overlap between the donor and acceptor. So when we deal with it depends what we are dealing with. We have the radiative and the non-radiative. If we have the quencher, then we have the quenching constant also play a key role. We have intersystem crossing also play a key role. We have energy transfer, also play a role. So everything it depends on the solvent and the probe and what we are studying. That's more important. And then fluorescence lifetime, as I mentioned earlier, fluorescence lifetime is the average time of the molecule stays in the excited state. So when we excite the molecule, it goes to the molecule goes to the excited state and it stays there for a certain time, and then it emits its photon and returns back to the ground state. The measurement of fluorescence lifetime, we use the technique called the time correlated single photon counting. It's a very simple technique. I will explain to you in a layman view, but it's not very simple like as I explained to you. It's very complicated system, but it works in a very simple principle. It's similar like that. I take same photon and separated into two. I take a same photon and separated into two. Okay, and then one passes through the sample, another it doesn't pass through the sample, and we have two detectors. One passes through the sample. The same photon passes through the sample. Another photon it doesn't pass through the sample. I can measure once I stop. start the photon from the source. This is the start. Just one passes through the sample, another it doesn't pass through the sample. It passes like this in another pathway. It passes through the sample. So when it reaches here, the detector, I can stop the stopwatch. So I can measure the time it traveled from year to year without the sample, and year to year with the sample. The difference between the time difference, I can calculate it. This time difference, I can, for each photon, I can accumulate it like a histogram, and then from the histogram, I can find out the lifetime. So it acts like a small stopwatch. So we have two different stopwatches for the same photon. We stop one stopwatch when the photon comes to the stopwatch directly. Another one when it comes via sample. So the time difference between these two, we measure it, and from the time difference, we can plot the we can accumulate for each photon like this, and then from the we can construct a histogram. From histogram, we can fit it by exponential or single exponential. From that, we can measure a lifetime. But as I mentioned, a very simple way, but the system is not that simple. It's a little bit complicated, but it works like that only. So what is time resolve measurements? We do the fluorescent measurements in a two different way. One is the steady state measurement, another one is a time resolve measurement. Steady state measurement, it's just watching from the stage. When horse race is going on, just we can watch it from the, we can sit in the stage and watch it. That is a steady state. Another one, we can take the camera in the jeep and watch the race with the time. So I move along with the horse and record it each and every second, and then we can see it. In some cases, you see it. For horse, all the four legs are in air. But if we watch it from the stage, we never see these kind of events. But if we have a very fast camera and a very fast jeep, better than the horse speed, then we can able to catch each and every movement of it. That is called a time resolve measurement. So for time resolve measurement, two things are very, very important. The source also high speed. It's if I want to watch the picosecond time resolution measurement, then I need a source with the femtosecond. And the detector also, the detector means it's a camera. The detector also, it's very efficient to capture the each and every movement of this kinetics. For example, for ear odds, their molecules, we are going to see the kinetics in each every seconds. For T0, T is equal to 1, T is equal to 2, we can see it and find it out. It means we are moving with the molecule and see what the molecule is doing with the time. In the femtosecond time scale or picosecond time scale or nanosecond time scale, depending upon the source, depending upon our detector, we are going to see what the molecule is going to do. This is called a time resolve measurement. So if we take the fluorescent spectrophotometer, it differs a little bit from the absorption spectrophotometer. So in all the spectroscopy, two things are very, very important. Three things, for example. First is the source. Another one is the detector. Another one is the sample, the one we are going to measure. Now, all the spectroscopy, you see the source, you see the detector, you see the sample. Only the source and the detector is going to vary. What you are going to see, what you want to, based on the source may be different, based on this detector may be different. In the case of absorption spectrometer, the light passes through the monochromator. Monochromator is nothing but like a prism. It separates the sun white light into the color line, like blue, yellow, Vibgyor, like this. It separates the light. So we can pass only certain wavelength through the sample. And then in the case of absorption spectrophotometer, we are going to measure the transmitted light. So we have the detector here. In the case of fluorescence study, we are not going to measure any transmitter light here. We are going to measure the fluorescence coming out of the sample. Fluorescence is isotropic. Isotropic means I can measure it from here. Here I will get the same number of photons. So isotropic. So we can place the detector in the perpendicular. The detector is here. You see, we have the one more monochromator, but from this monochromator we go to the detector. the detector is perpendicular to the excitation source. In the case of absorption spectrophotometer, the detector is parallel to the sample. So any spectroscopy, the light source and then sample and the detector is important. Monochromator it separates the wavelength from the white light or xenon lamp. Normally in the fluorescence spectrometer, we use the xenon lamp. From the xenon lamp, it separates the light. And then we have the filter and then slits polarizer. I will explain to you little by little. That's a very simple diagram. This is a little bit complicated diagram. We have a different inside we have a lot of components like this kind of mirror and focusing and then excitation monochromator, emission monochromator, chromator. Lot of parts are there, but you see, this is the real one. We have the xenon lamp. The xenon lamp emits the light and then it passes through the monochromator. Monochromator separates the wavelength of the light and then it passes through the grating. Grating allows only certain wavelength passes through it, and then you see it passes through the polarizer and then it passes to the sample. From the sample, it can go to the U visible detector or a NAR detector. Depending upon the detector, we can that is sensitive on the wavelength. If we want to measure the IR radiation, we need a NAR detector. If we want to measure the U visible radiation, then we need a normal PFT or. So when we excite the sample, normally we excite it in the absorption maxima. When we excite it, we are exciting at 450. You see the emission occurs at 650. Always in the longer wavelength than the absorption maxima. The emission always occurs at the longer wavelength. For a fluorescence spectroscopy, we can use any kind of samples. We can use a solution. We can use thin films. We can use powders. We can use crystals. For all kind of measurements, we can able to do it. Only thing we need the sample holder in the cell compartment is able to measure the powder sample or thin film holder or crystals. Those kind of things very important. When we record the solution and the wavelength of the light is passed through the sample and we are going to measure it. The emission we are going to measure it. Always we are going to measure it in the perpendicular region. When we record the what are things we have to take care of it? When we use the solution sample, we have to take care of the concentration. We use the very high concentration. When we excite the molecule, not all the molecules goes to the excited state. Only few molecules goes to the excited state. When we emit the photon, if you have too many molecules in the solution, the molecules neighboring to the emitting molecule absorbs the light, and we will get, for example, if we add the 100 molecules to the excited state, we will get only, if we have too many concentration, we get the emission from only 30-40 molecules. If we have very low concentration, if we excite the 100 molecules, we will get emission from more than 60% of the molecules. So the cell quenching, we have to take care of it. That is, we call the inner filter effect. For example, if you see the anthracene molecules, if we use the higher, the very low concentration is the micromolar. Here you see it in the millimolar. The intensity of the millimolar solution is lower than even though we have a lot of molecules in the solution, in the anthracene solution, the emission intensity is lower than the micromolar solution. So it's better to keep the absorbance always lower than 1 in order to avoid the inner filter effect. When we work with the solid samples, the solid samples always give the second order spectrum. Second order spectrum means, for example, here I am exciting at 380 nanometer. Second order just to multiply into 2. So 600, 160, so 760. You can see the 761 now. It's not due to the emission. Some people think that it's emission. It's not an emission. It's from the second order pattern. So second order pattern we can eliminate it. We can correct it and to get the correct emission spectrum. So when we record with the solid sample, we have to be very careful with the excitation wavelength and the second order spectrum. And then thin films also, solid also use the thing. Well, how we can avoid it? We can use the filters in order to cut it. We have the different kind of filter, long pass filter, short pass filter. Long pass filter means above here if you see it above 500 nanometer, all the wavelength passes through the filter. So here if you see it, short pass filter means it passes only between 300 to 500 nanometer. After that it blocks everything. So this is the long pass filter. If WG305 means it's a long pass filter. So long pass filter means it after 300 nanometer it passes everything. After 395 it passes everything. After 500 it passes everything. After 590 it passes everything. After 700 it passes everything. So we can use the different kind of filters to cut the second order pattern or range scattering from the solution. Those kind of things we can able to do it. This is the band pass filter. Band pass filter, the long pass filter and long pass filter, it passes everything. In the case of band pass filter, it passes only certain band. It passes only 400 to 700 nanometer. Below or above, it cuts everything. So it's the so filter we can use it for remove the second order pattern or value scattering from the solution. Then slit. The slit also very important criteria. The slit always be there before the sample. This is a shutter. You can see the entrance slit here and then exit slit here. So if you open this entrance slit too much, we can pass the large number of photons to the sample. So if we pass large number of photons to the sample, we can collect large number of photons also. Here also, if we increase the slit, if we open the slit too much, then we can get all the photons to be empty. This is the slit. By adjusting the slit, we can move this place. We can have a narrow slit or wide open slit. You can see it's wide open. It's a very narrow slit. So when we open the slit with more light hitting the sample, more emission, more light hitting the detector also. So more signal, greater signal to noise ratio. These are the advantage. But the main problem here, when we increase the slit width, the spectral resolution, the wavelength resolution also decreases. But the resolution decreases. When we increase this is the monochromator, it separates the wavelength of the light. When I increase the light, if I want to pass only 400 nanometer through the slit, if I increase the slit width, not only 400 pass through the sample, it's 405, 402, 405. In the same way, 398, 396 also passes through the sample. So we lose the spectral resolution, the wavelength resolution. You see the slit width is 0.5 nanometer, the band pass is 2.125. Thus, when we increase the slit width, the band pass also increases. So if you are more keen on the wavelength, then you should use the minimum slit width. If you are not keen on the wavelength maximum or spectral resolution, you can use the higher slit width. For example, if the quantum yield is very low, no other option. You have to use the higher slit width only. But if you have a higher quantum yield, you can use the low slit width option. You see that the spectral resolution is the low slit width, you have a better resolution. You see the full width of maximum is higher if you use the large slit. The wider slit width, you can see the emission 1, emission 2, emission 3. So it's when we increase the slit width, the emission intensity also increases. At the same time, you see the full width of maximum also increases. You see the small slit width. It depends. The bandwidth is only 2.1. Here you see the 8.5 nanometer. So we should be very careful with the slit width. Well, what we want to measure it. Based on that, we can decrease the slit width or we can increase the slit width. We can play with it. Another one is a polarizer. Polarizer is especially for a biomolecules. You see the polarizer. People always use the polarizer before the excitation as well as after the emission also. This is the sample. This is the excitation, and then here the emission. Before the detector, we use the polarizer. Before the excitation, also we can use the polarizer. So the light always non-polarized. For example, if we use the laser source, is always polarized, but the xenon lamp coming from the is non-polarizer. When we use the polarizer, we can polarize the light, whether it's a vertical or horizontal parallel, horizontal or vertical, we can polarize the light. When we polarize the light, molecules orient in the same direction. For example, my polarization of light is like this. The molecules orient in this direction only absorbs. The molecule orient in this direction, it doesn't absorb. So this is the only molecule orient in this direction only absorbs. When we during the within the emission during the lifetime of the excited state, the molecule oriented in this direction may rotate. Maybe undergo fast rotation or slow rotation. If the molecule undergo very fast rotation, we cannot see it in the polarization anisotrope. But if the molecule is heavy and it's very slowly rotate, we can able to see it from the anisotropic measurement. Those kind of things we can see it. You can see the molecules always in the solution. It orient in a different direction. If I use the plane polarized light, this is the unpolarized light. If I use the plane polarized light, I can get only the light in this direction. Only the molecules orient in this direction. This molecule only orient in this direction. So it only excites. All the molecules it doesn't excite. So during the excited state, you can see the molecule may reorient based on the rotational correlation. It can change. So we have the detector. We have you see in the anisotropy equation, you can see one eye parallel, two eye perpendicular. Two eye perpendicular because when we excite the light, we have two perpendicular positions. The intensity dissipates into two different directions. That's the reason we always have a total intensity is equal to one eye parallel, one eye perpendicular. Because parallel is only one, but the perpendicular is two. So we have two perpendicular. From this, we can calculate the anisotropy rotation correlation coefficient also. So normally this kind of anisotropy is very useful when we deal with the biomolecules like proteins, enzymes, because these proteins and enzymes rotate very slowly. But organic molecules we cannot do any anisotropy because it rotates very fast. The anisotropy we cannot get any anisotropy from it. But when we have a biomolecules, it's big. When we excite it, it rotates very slowly. So when we record it in parallel or perpendicular direction, we will get a different kind of intensity. From this, we can determine a lot of factors about these biomolecules. So we can attach the fluorophore to the biomolecule and record the polarization. So if this is a large DNA, for example. If the DNA cleave, if any enzymes cleave the DNA, then it becomes a slow molecules. So before cleavage, these molecules, so higher anisotropy, after cleavage, this molecule also rotate very fast because it's very slow. So we cannot get any anisotropy. From this, whether we can find it out whether the cleavage is occurs or not, the enzyme works or not, those kind of information we can get it from it. Other sampling accessories, spatial imaging. Spatial imaging is only for a confocal microscope or microscope application. We can use it, and then cryostat we can use it to measure the fluorescence intensity at a very low temperature. And another thing is the integrating sphere. Integrating sphere, we use it for measuring the quantum field of the sample. These are the other accessories we use it. Microfluidic reader for biomolecules. These are the other accessories we don't have to worry about it much. Only thing we have to care about whether the solvent impurity is present or not. We have to be very careful with the Raman bands. Self-absorption, when we're dealing with the solution, we have to be very careful with the self-absorption. We have to always use the absorbance lower than 1. And then we have to be very careful with the Raman bands. Raman bands, most of the time, it will cheat the people. They think it's emission, but normally it's not the emission. And then with the instrument we can play whether the instrument stay light may come, split may be higher. Depending on that, we can play with the signal to noise ratio. So few application I can mention. Normally the fluorescence is used for sensing applications. The people are using for sensing nitro explosives or lot of things people are sensing it. Advantage is it's very easy and easy to detect, and you can see the color change very easily, and it depends on the solvent, polarity, environment. So and also it detects in the within a ppm number parts per million. So that's the one cases. Another one is the cancer cell migration. Normally, when we remove the cancer cell, it migrates from one place to the other. So whether the cancer cell migration occurs or not, we can take the time lapse image and then we can find out whether the cancer cell migrating or not. This kind of information we can get it. Another thing, the important thing the people nowadays working on is the cancer cell markers. Uh, because when the doctors when they do the surgery, it's very difficult to find out whether it's a malignant tumor or it's a normal cell. It's very difficult to find it out. The malignant cell also it looks like similar. You can see this is the malignant tumor, but it's very difficult to see it, okay, with our eye. But when we have the microscope and when we see it, we can cut it exactly. You see it within this. This only the malignant tumor. We can remove only this area. It's more than enough. We don't need to remove all the cells around it. So in this case, for marking cancer markers, lot of probes are used. These are the important things. And then don't worry about it. All the slides I used, I took it from only two things. You can search Ken Onsen. Ken Onsen presentation only. I took all the slides from it. So most of the slides you can get it from it. It's available in Google. You can search it. And then another slides I took it from the Principles of Fluorescence Spectroscopy by J.R. Lakowitz. It's like a Bible for fluorescence spectroscopy. Some of the images I used from our own students in Satyaraj and Suhasini. Other than that, everything I took it from Ken Onsen and J.R. Lakowitz book. If you want to understand fluorescence better, just go through the Lakowitz, you can understand it better. It's like a Bible. Thank you very much. If you have any questions, I am happy to answer to your questions.
Am I audible, sir?
Yeah.
Okay, sir. Thanks a lot for your excellent talk, sir. Very informative talk and fundamental things you have discussed. First of all, I would like to thank for your kind acceptance of our invitation and your excellent talk, sir. So we have received some question in chatting box of YouTube as well as Zoom link. Can I read that question, sir?
Yeah, sure.
Okay. This question asked by Bhumiha Banerjee from Tripura University. She asked about why fluorescence spectroscopy is more sensitive.
The fluorescence spectroscopy is more sensitive because it's more sensitive to the environment. Because when the solvent, mostly we are playing with the organic molecules. The organic molecule, most of the organic molecules, not all molecules are very sensitive. For example, if I take naphthalene or anthracene, it doesn't very sensitive to the environment. Okay, when we take polar molecules like DNS or fluorescein and the other molecules like DMAB and dimethylaminobenzoate, it's well known charge transfer molecule. More than 1,000 population came from this one single molecule, DMAB, and you can search dimethylaminobenzoate. It's nothing but one phenyl ring. In the top we have N dimethyl group and then one cyanide group in the bottom. So one donor and acceptor are connected through the benzene ring. If you see it, this molecule shows a very interesting feature like a dual emission. So the molecule undergo exotic rotation in the donor group, and one molecule emit from the planar structure, another molecule emits from the twisted structure. So in the twisted, the donor is decoupled from the acceptor. So the charge transfer occurs through the space. So that's a twisted intramolecular charge transfer, and that wavelength and the structure emits at longer wavelength than the normal emission. So it depends on the molecule. If you have a more polar molecule, it's very sensitive to the environment. Another thing, the detection is very. For example, from my opinion, within few years, Raman spectroscopy will take over the fluorescence spectroscopy. The Raman spectroscopy is very sensitive compared to the fluorescence spectroscopy. But the Raman spectroscopy, still the instruments are very expensive. The detectors are expensive. The sources are expensive. You have to spend minimum 1 crore to get a spectrophotom, Raman spectrophotometer. But in the case of fluorescence spectroscopy, you can get the cheapest instrument from 5 lakhs to, there is also there 5 to 25 lakhs you can get it. It's compared to Raman, it's very cheaper. One thing, and it's very easy to handle. You can use the fiber to measure the fluorescence from any solution, and you need a very small probe is enough, because here we are not going to measure the scattering. We are measuring the emission from the sample. In the case of Raman spectroscopy, we are measuring the scattering light. So the scattering is very low. The intensity is very low. We need a high sensitive detector. We need low. We have to take care of a lot of things. But in the case of fluorescence, we don't have to take care of anything, because we are not measuring anything a straight line. We are measuring in the perpendicular direction. That is we are measuring the emission coming from the sample on the perpendicular directions. And also the quantum yields of these probes are very high, and it's very sensitive to environment, and the probes are very small, and we can tag anywhere, and we can bind with any DNA molecule or protein molecules, and it's not carcinogenic. A lot of advantage for fluorescence molecules. And in addition to the fluorescence molecule, the FRET also is very important. We couple the donor and acceptor with the biomolecule. We can, during the enzymatic activity, we can see the fluctuation of the enzymes also. The enzyme activity, how long does it take the substrate to bind with the enzyme? How long does it take the enzyme? How long the enzyme takes to carry out the reaction? That the substrate converted, the reactant is converted into product. How long the product is stayed in the binding pocket of the enzyme? How long does it take the product release from the binding pocket to the solution? All the things we can get it from fluorescence spectroscopy. That is the advantage of it. Not all probes are very sensitive. Only few probes are sensitive. The fluorescence spectroscopy compared to Raman spectroscopy, fluorescence spectroscopy is very. A lot of people are using it because of this cost effective, the easy to handle. It's very sensitive. We can detect whatever we want to detect. We can detect in the parts per billion or parts per billion. That is the advantage people use the fluorescence spectroscopy.
Thank you, sir. And this question asked by Prakash from Vivekananda College, Thiruvedagam, Madurai. Sir, while organic dyes having photo bleaching, it is the major drawbacks. Can you explain how to avoid this photo bleaching?
Photo bleaching, a lot of people are working on photo bleaching. Photo bleaching is the understanding the photo bleaching itself. A lot of nature science papers are there, because photo bleaching is a major drawbacks. That's the reason. For example, if you take a ruthenium bipredyl molecule, and if you shine the light for a few days continuously, also it doesn't photo bleach. That's the stability. That's the reason in the dye sensitive solar cell, lot of people, whoever in India worked on dye sensitive solar cell, they use the ruthenium bipredyl complex, because the ruthenium bipredyl complex is very stable, photostable, very strong photostability. It stays for days. You can shine a light. It stays longer. But the organic molecule, as I mentioned, it has a photo bleaching ability. But not all the molecules. It depends on the molecules. Photo bleaching, we can take it in an advantage or a disadvantage. Both way we can take it. For example, in the single molecule microscopy, if we want to get a better resolution, we use the photo bleaching to get a better image. Because we bleach, for example, if we take a donut shape of high intensity beam and bleach the molecules around that region, and we get a high resolution. Because in the first microscopy, the resolution is lambda by 2. For example, if I use 400 nanometer wavelength of light for excitation wavelength, I can get the resolution of only 200 nanometer. I cannot go below that. It's a physics, based on physics. We cannot go diffraction limited volume. So it's lambda by 2. In order to go below lambda by 2, a lot of people use the photo bleaching as an advantage also. So photo bleaching has its own advantage as a disadvantage. Photo bleaching we can avoid. For example, if you have a probe with a lot of nitro groups or acceptor groups, these molecules photo bleach very easily, especially the nitro molecules containing nitrogen moieties are very unstable. That kind of we can play with. If you are an organic guy, you can play with the substituents also in order to avoid photo bleaching. But a photo bleaching, it's a one criteria of the molecule. We cannot. It not only one criteria of the molecules. It's a lot of. It depends on a lot of factors, but we can play with it. That's only I can say.
Thank you, sir. And this question asked by Logesh Kumar, MSc student from Crescent University. He asked about how red shift and blue shift depends on the polarity of solvent.
Polarity of the solvent. Not all molecules play polarity of the solvent. For example, if I take the naphthalene or anthracene, if I take naphthalene or anthracene and dissolve it in a different polarity of the solvent, it doesn't show much shift. So it depends on the molecule first of all. So if you have any donor acceptor kind of molecules like DNS or DME, these kind of molecules, when I excite the molecules, the charge transfer occurs from N and dimethyl. This is the donor, this is the acceptor. Through bond, the charge transfer occurs. So when the electron transfer from here to here, it becomes del positive. Okay, this becomes del negative. In the ground state also some charge transfer is there. For example, if it's del positive, del negative in the ground state, in the excited state it's del positive, del negative. So the charge transfer is more in the excited state. When we have the solvent reorient in the excited state. If I have a toluene in DNS in toluene, the toluene is nothing, no role. It doesn't have any polar moiety in this solvent. It doesn't play any role. So blue shift will absorb because whatever the charge transfer is there, charge recombination occurs and the molecule return back to the ground state quickly. So, but in the case of if I take a DMSO or a DMF or butanol, we take the butanol here because butanol, it's as a OH, it's a polarity. It's a polar del plus and del negative in the solvent itself. This del negative in the solvent surround this del positive. Okay, and then del positive in the solvent surround this and stabilize this charge transfer in the excited state. The charge transfer is more stabilized. Stabilization means lower energy. Lower energy means higher wavelength. So we will see the red shift. So when the case of destabilization, in the case of toluene or hexane, we can see the blue shift because it's a destabilization. In the case of butanol, it's a stabilization. That's the reason we can see the red shift. Am I answered correctly?
Yes, sir. Thank you, sir. And I have some questions, sir. Actually, you discussed about the Stokes shift.
Oh, one person raised one student raised the question hand also. First, we will answer that person question.
Okay, sir.
Can I able to see it here?
Wait a second.
Who raised? Maybe from the audience, some person raised. One lady.
Admin, give a chance to the participants to unmute their mic by themselves. Who raised the hand? The participants, please talk to our chief guest directly.
Feel free if you want to ask in Tamil also, it's okay. I will answer it in Tamil. So don't be shy. This section is only for you. So I see one lady raise the hand. That's the reason I asked it. If it's not the case, we will go for it. So she
Yes,
can
sir.
ask.
Sometimes by mistakenly they raise the hand, sir.
Okay.
So we given the provision to unmute mic by themselves, but not that. Okay, sir. Actually, based on the Stokes shift, for example, the Stokes shift, if it is more than 100, people are saying that it is highly fluorescent, and less than 100, very sharp peak is obtained. So what information we can get from the
Stokes shift, you cannot say it's highly fluorescence or weakly fluorescence because some of the organic people, they misunderstood these things, they give you wrong information. So from the Stokes shift, we can see the application of the molecule. Okay? If the molecule shows a large Stokes shift, then when we can use it for bio applications because it doesn't interfere with the core molecules present in the biomolecules. That only we can say it. But if we want to say exactly it's highly fluorescent or weakly fluorescent, we have to measure the quantum rate. And also the highly fluorescent, weakly fluorescent, it's always a comparison. So compared with what? That's very, very important. Okay. For example, if I am taking the fluorescence quantum yield toluene and if I take the fluorescence quantum yield butanol and the butanol, the quantum yield is high compared to the toluene, then I can say it's highly fluorescent in butanol compared to the XA. Okay. So it's always comparative. Or if I compare with the fluorescein, I can say my molecule is higher quantum yield than fluorescein, so it's highly fluorescent. So based on the wavelength, we cannot say whether it's highly fluorescence or weakly fluorescence. We can say only it's blue shifted or red shifted. It has a large Stokes shift or uh, less Stokes shift. Those kind of information only we can say it from the.
Okay, sir. And what about the full width half length maximum? Based on the same concept, we can able to say if we are getting full width half length maximum broadband.
Maximum it depends. If you have two close line peaks, you always get the two close peaks merged together. If the emission coming from the two states, two close line peaks, these two emissions merged together to form a broad emission. Okay? This broad emission gives a high full width of maximum. And also high with the full width of maximum is higher in the case of if I use the largest slit width also. So it depends on the condition I'm using it because I'm using wavelength resolution or spectral resolution there. If I use the large slit width, in this case I will get the full width of maximum is higher compared to the lower slit width. So from the slit width also we cannot say, from the full width of maximum also we cannot say anything. If you have the laser, we can say from the full width of maximum exactly. But these kind of fluorophores, the fluorophores emission coming from the two close line state or single state, it's very, very important. If we understand those things, then we can say from something from that. Otherwise, it's very difficult to see. If whether you see it here, we have a two close line peaks. Okay. These two close line peaks in the higher polar solvent, it's merged together. You see it here. We cannot see this peak here. If you see it, this is one peak. This is one peak, and these two peaks merged together to form a shoulder. But the shoulder is completely disappeared in butanol and ethyl acetate because these two have the same kind of intensity, so merged together. We cannot see the shoulder. So I cannot say from the full width of maximum the quantum yield is very high or it emits a lot. So it's very difficult to say.
Okay, sir.
Did I answer it?
Yes, sir. Yes, sir. You are correct, sir. And this question asked by Dhyaneshwari from Crescent University. How to increase the fluorescence lifetime of nanomaterials?
It's very, very difficult. Nanomaterial, we can play with the doping. Okay, the material we dope in this way we can increase. And then if you are playing with the whole and charge recombination, you can stabilize this in some way. The doping material, you can stabilize this recombination. When you stabilize this recombination, it stays for a longer time. The recombination is very fast, whole charge recombination is very fast, then it comes to the ground state very easily. This way you can play it also.
Thank you, sir. And this question asked by Pooja from Riyadh Bakra University, Sandikar. Sir, fluorescence spectroscopy can be a correct technique to use for the quantification of amount of drugs that is conjugated on a nanoparticles.
Conjugated on a nanoparticle, it's very difficult to say what kind of nanoparticle and the size of the nanoparticle also. Sometimes you can get the scattering also. The scattering, if the scattering is high, it dominates the fluorescence. So if the scattering of the it's a second harmonic, the scattering will be like this only. Okay. If the scattering is very high, you think that this is a emission, but it's not a emission. So the most of the time, nano emission from the nanomaterials we cannot quantitatively we cannot say it. If you record the same solution at a two different time, you can make the two different kind of emission density, or the wavelength may shift because the particle scattering may be different from solution to solution, and the number of particles, it depends on everything, and that the particles are uniformly solubilized. A lot of factors are involved, so it's very difficult to quantify it from my own experience. I never use it for quantification, but I can use it as a qualitative. For a qualitative purpose, we can use it, no problem. For a quantitative purpose, I'm not sure about it.
Thank you, sir. And this question asked by Shanti. Sir, can you explain about the statistic or dynamic quenching? How their peaks will appear in Sternwalmer plot?
A Sternwalmer plot is only for a dynamic quenching. Okay. If you are playing with the Sternwalmer equation, then you are not going to talk about the static quenching. Static quenching, dynamic quenching only we are going to use it. Some cases, what happened, both static and dynamic quenching occurs together. In this case, Sternwalmer deviate little bit. Okay. Otherwise, the Sternwalmer equation only for a dynamic quenching. You never use it. Never use the Sternwalmer for static quenching. Static quenching, you can understand it very easily from the absorption spectra. If static quenching occurs, and the absorption spectrum will change. In the case of dynamic quenching, the quencher interacts with the fluorophore only in the excited state. So the dynamic quenching occurs only in the excited state, not in the ground state. So that is the way you can differentiate, and you can measure the fluorescence lifetime also. In the case of static quenching, the fluorescence, when you add when you increase the concentration of the quencher, the fluorescence lifetime doesn't vary. But when you in the case of dynamic quenching, you can see that when you increase the concentration of the quencher diffuse very close to the fluorophore, so that fluorescence lifetime also vary. From this, you can differentiate both static and dynamic quenching. But when you discuss about Sternwalmer equation only for a dynamic quenching. If you want to understand this better, the Lakovic's book is the best one. Go through it, you can understand it very clearly.
Thank you, sir. And this is the last question. Satya from Crescent University. Sir, what information we can get from isobestic point?
Isobestic point means for example, I take a probe A. It interacts with the analyte B. Okay, A and B form a complex. Okay. The B doesn't absorb in that wavelength, so A only absorbs in that wavelength. So A binds or reacts with B to form AB. Okay, so we have in the solution we have two different equilibrium. A also there, AB also there. Okay, the isobestic point is nothing but the absorbance of A and AB both are equal. That's all. In that wavelength, the absorbance of A and AB both are equal. Am I answered the question?
Yes, sir. Thank you, sir. And if you don't mind, two more questions are there. It's interesting question. So myself first wants to know the answer for that one. What is synchronous fluorescence? Where it is applicable?
Synchronous fluorescence. So where they want to measure it? Synchronous fluorescence, where they want to use it?
Actually, the people are using for a binding of DNA and as well as the binding of proteins. There they are using, sir.
Yeah, a lot of people they are misunderstood the synchronous fluorescence when people they bind with the DNA complex or protein. They misunderstood.
Yeah, that is why I am asking, sir. You are correct person to explain these things.
I have a lot of doubts in it. I asked my own student also whenever they presented the SNAPS thesis. The synchronous fluorescence they use it. From my opinion, it's not very correct.
Okay.
A lot of people they misunderstood it. They interpret wrongly. That's the thing, from my opinion.
Okay, sir.
we have some spectra, we can discuss about it.
Okay, sir. And this is the last question. So in some paper, people have been reported excitation spectrum and emission spectrum. And few more papers, they are reporting absorption spectrum and emission spectrum. Excitation spectrum and absorption spectrum both are same.
It's not the same, because absorption spectrum, we are seeing the excited state from the ground state. So we are exciting the molecule, but the excitation spectra is we are seeing the ground state from the excited state. It's totally different. The absorption and excitation spectra are similar when the molecules can I say it? The molecular structure is same in the ground state as well as the excited state. We can get the same absorption as well as the emission spectra. In some cases, the molecule undergo excited state reaction to a different species. If the two species are emitting, then the excitation and absorption spectra it doesn't match. So that's the thing. But excitation spectra and absorption spectra, these are two different things. We are seeing the ground state molecule from a two different perspective. For example, if I asked about me to my students, they tell this, they tell something, and if you ask to my mother, she say something, but I'm different person. So it's the same person, they interpret it differently. This is the way we see the molecule from the different perspective. Only the perception is different, and we see that we get the different information from the excitation spectrum. We get the different information from the absorption spectrum. So it's not the same.
Thank you so much, sir. On behalf of our Crescent family as well as Summer Internship family, it's my pleasure to thank you. Thanks a lot for your answering of all the questions. Do you want to say anything to our master students, sir? Please, sir.
Nothing to say. Just you try to find it out yourself. What's your interest? Okay. I don't say the PhD is the goal. Okay? I always say to my friends, each and every job is equal. It's my job or a cleaning lady job. It's both are equal as long as I fully involved into the job and I put my soul into it. Then I do better. Whether it's the cleaning job or the teaching job, it depends. Okay? So you find out your interest and put your soul into it. It's not like you cannot do it just for your teacher. Because my teacher told this, so I'm doing it. It's not the case. Okay? You find out your own interest and go with your goal, go with your motivation, go with your for research. The curiosity is very important. The curiosity and the creativity is more important. You have to think differently. You cannot follow someone. Okay, you cannot. If you follow someone, you will be in the same direction. You have to think differently. Your perspective will be different. You have to think differently. And it's not the case everyone tell, okay, you are studying MSc, you have to go for a PhD. I never say that. Okay, PhD is not for everyone. It's not if you feel PhD is not your cup of coffee. You cannot taste it. Okay, if you like tea, how do you like the coffee? Okay, it's the same for PhD also. For company job also, it's same. If you want to do an academic research, if you want to do an independent research, you cannot survive in the industry, because the industry, someone says this one and you have to repeatedly, you have to do it. So you have to follow it. That's all. But in the independent research, you have to think yourself and you have to find out the solution for it. Most of the days, you will not get the result. Because if you do TPM research for 360 days, you get the 20-30 days, you will get your result, expected results. Otherwise, you cannot. If you are repeating the same thing, then you can get the result every day. But if you are doing something novel, you never get it. Now, some day you get it, but you cannot interpret it. You have to think about it for a few days in order to find it out. For research, the patient is very important. The guide is secondary. From my opinion, the guide is secondary. That's the reason they never call it as a teacher. For a PhD, they call it as a guide. Just he or she will guide you to do your work. But you have to do it independently. It's your PhD, it's your research, it's not your guide thing. So just you during your undergraduate or post graduation, you try to find it out your goal and move towards your goal. After a few years, if you find it out, chemistry is not your cup of coffee, just to change it. Nothing wrong in it. Okay. If you like computer or if you like a software job, just to go for it. Nothing wrong in it. For example, if India, so many people are doing, everyone is surviving, everyone is getting a job. It's not the case, because whoever they put the soul into it, they are surviving. The same way for all jobs. Uh, all jobs are equal. Uh, don't compare you with anyone. Okay, you compare you with yourself. Yesterday, if you learn it something, today if you learn a different thing, and if you correlate these two, that's very important. Okay, that's more than enough. Just to compare you with yourself each and every day, and yeah, improve little by little, and you will master. And your basics are very, very important. Whatever you are doing, PhD, just once you build your basics, you can survive anywhere. It may be in chemistry or physics, biology, it doesn't matter. Your basics should be very, very strong. So when you read it, when you study it, put all your soul into it. Don't do it for someone, do it for yourself. That's only I always say to my students. Uh, and don't compare with anyone. You are not here to compare with anyone. Each and every one is unique. You don't have to compare you with someone and feel better. You compare yourself uh, compared to yesterday, and if you are feeling better, if you do it better, if you feel proud of yourself, that's more than enough. That's your soul should feel happiness. That's more important than the other soul. So, and the same way, all jobs are better, whether it's a banking job or a cleaning job or research or a company. All jobs are equal as long as you are interested and you put your soul into it. Uh, the, that's my perception. Okay, that's my opinion. Always, it may be wrong. It depends on the people. The perception may vary. Think yourself. You ask questions yourself. You get the answer for it. First, to try to find out what do you want. What do you want to be? Why? Get the answer for yourself. Then you go towards it automatically. You will not have any problem. This is my suggestion or opinion. You can take it whatever way.
Thank you so much, sir, for your nice word and encouraging words, as well as the excellent talk and answering for all the questions. Now I request Nivedita to deliver a vote of thanks.
And one more thing,
Yes, sir. Yes, please,
if
sir.
any students or anyone wants to ask anything, any question, or need any clarification, feel free to contact me. You can find my email address or phone number in the website. My name is Tyagarajan, so you can find it in Bhardas University website. You can ask me. You can ask me at any time. Okay, you can write to me or you can call me. Just if the call comes from the unknown number, most of the time I will not answer it. So just test me before. I am from this college, I need this. Shall I call you like that? Okay, then I will answer it. Otherwise I will reply to your message also. Most of the time unknown message means I will not answer it before testing. So you are a student, normally student means I will answer it, no problem, anytime. Otherwise I will return back to you. So feel free to contact me at any time related to your subject or any clarification or any. Thanks one and all. Thank you very much.
Thank you, sir. Nivedita.
Yes, sir. Gratitude is the healthiest of all human emotions. The more you express gratitude for what you have, the more likely you will have even more to express gratitude for. It's my honor to deliver the vote of thanks today. On behalf of the management of B.S. Abdul Rahman Crescent Institute of Science and Technology, I convey my sincere gratitude to our Chief Guest Professor Dr. B. Tyagarajan for his wonderful presentation. First of all, thank you so much, sir, for accepting our my invitation and graced the session with your invaluable time. You began the presentation with Jablonski diagram, followed by singlet and triplet excited states and fluorescence and phosphorus emission, and explained homo-lumo concepts. You also explained Kasha's rule and mirror image rule, which was quite new to us. You added some clarity to the already known concepts like Stokes shift and quantum yield. Time resolved measurement, filter effect were also aspects of your presentation. You made the fundamental concepts as even stronger than before, sir. That was an immaculate presentation, sir. Thank you so much for being here with us today. I also like to thank the conveners of the program, Professor Dr. S. Kuttirani, Dean, School of Physical and Chemical Sciences, Professor Dr. G. Ishwaramurthy, Head of the Department of Chemistry, Professor Dr. N. Basimalai, Coordinator, for organizing this internship and also for being constant support and motivation. I finally thank all the participants for the presence and keeping the session active with their questions. I once again express my gratitude to everyone. Thank you all.
Thank you, Ananda. Thank you very much. Very nice.
Sir, please stop sharing, sir.
Oh, okay.
Thank you so much, sir. We will be moving for next session. Yes, sir. If you want to stay here, no problem, sir. Otherwise, we can.
No.
Okay, sir. Thank you so much.
Did I stop it already, or is it okay?
Yeah, I did stop it now. You just
Okay.
click the leave button.
Oh, okay.
Leave. That's all. Nivedita.
Yes, sir.
Yes.
Now, let's move on to the second session of this day. Words can explain how much honored and excited I am to welcome and give the introduction about our most lovable professor, Dr. N. Basimalai. To be inspired is great, but to be an inspiration is a honor. Sir is definitely an inspiration to many of us. He's constantly inspiring us and hope we all become an inspiration as inspiring as he is. Professor Dr. N. Basimalai is now working as an assistant professor at Department of Chemistry, B.S. Abdurrahman Crescent Institute of Science and Technology, deemed to be a university, Chennai. He has completed his UG and PG degrees in chemistry at Vivekananda College, Thiruvedagam, Madurai, and received Best Student Award for both the degree period. Then he completed his MPhil and PhD degrees at Gandhigram University, Dindigul, under the guidance of Professor Abraham John. During his PhD, he received UGC JRF and CSIR SRF fellowships from Government of India. After the completion of PhD degree, he worked as postdoctoral fellow at the National Cheng Kung University of Taiwan. Then he received globally renowned fellowship of Marie Curie Fellowship in Europe and worked at the International Iberian Nanotechnology Laboratory, Portugal, from 2015 to 2018. His research interests are to develop optical sensor systems for biomolecules and toxic chemicals by using fluorescent nanomaterials, development of electrochemical sensor for biomolecules and toxic chemicals by using metal nanoparticles and polymers, synthesis of fluorescent carbon nanodots and metal nanoparticles from food and agricultural wastes and study the biomedical properties, synthesis of iron oxide, inorganic nanomaterials and upconversion nanoparticles for MRI applications to develop a paper-based and electrochemical kit for the on-site monitoring of bio and toxic chemicals. So far, he had published 35 research articles in highly reputed journals with very high impact factors, and 2 more papers has been accepted to be published with impact factors 8.758 and 11.30. He had published 4 book chapters and also filed a patent for calorimetry detection of endosulfan. He has several projects going on under his guidance right now. So far, he had organized various events including National Science Day, Online Chem Quiz, International Webinar, and 14 days faculty development program on material science and nanotechnology. He is currently being the coordinator of PhD Research Scholars Monthly Seminar and is the Purchase Coordinator of Department of Chemistry, Crescent Institute of Science and Technology. Till today, he has given 42 special talks in various national and international conferences worldwide. His research work had been highlighted in Nature India, and another work was published as a cover page article in Macromolecular Chemistry and Physics. He is serving as an editor in Mayfair Journal of Chemistry and Chemical Engineering, Canada since 2016. He is a reviewer in American Chemical Society, Royal Society of Chemistry, Elsevier, Springer, Wiley, Taylor and Francis, Bentham Science, and Oxford journals. He is currently handling 4 PhD students and several master's students, including myself. He is also co-supervising one international PhD student from University of Mara, Malaysia. He has research collaborations in various countries, including America, Portugal, Spain, Poland, Taiwan, Malaysia, South Korea, and China. Professor Dr. N. Vasimale always says, winners don't wait for opportunities, winners create opportunities. Undoubtedly, Sir is an absolute winner who always comes up with unique ideas and has his own kind of style in making it work. He's a hardworking person as well as a smart working person. Nothing can stop him from his achievements since he is very much determined. I find myself so lucky to give his introduction about him and far more luckier to be the student under his guidance. I'm sure that the participants are excited as I am to listen to his talk on the topic of facile synthesis of highly red fluorescent gold nanodots as potential sensing tropes for environmental toxins. Without further delay, I hand over the session to Professor Dr. N. Vasimale.
Thanks, Nivedita, for your nice introduction. Very good evening to all. So, as you requested earlier, this is the time to deliver my talk. So, already I have given several talks in national and international level, but it is my privilege to give a talk in this summer, 1 month summer internship on recent advances in chemical sciences. So, it's a very nice topic. So, see these photographs. So after see these photographs, you may have little doubt. I don't know whether Vasimale sir is going to open the jewelry jobs because these much jewels are there. Wait a second, I can give my answer. And this is a golden temple Vellore. So the gold is mingled with our everyday life. And from the ancient days, people are started to use the gold. And also some quotes are there. See here, all that glitters is not gold. You are golden baby. You are worth more than gold. Stay golden, etc., etc. Why I am showing this one? So if we are working in a jewelry jobs, we will be very happy because if we are entering inside of the jewelry shops, especially ladies are very happy. Why? Because it is glittering, the glitter natures. I'm also very happy because I'm also working in the gold. So gold nanoparticles. Yes, today my topic is a facile synthesis of highly red fluorescent gold nanodusts as potential sensing probes for environmental toxins. Okay, let's see one by one. What is gold? So it is unknown one. Even we don't know who has discovered this gold. So from 300 BC, people are started to use. It has medicinal properties. So the gold appearance of yellow color and having the malleability, ductility, soft and dense nature and shiny nature. Because of the shiny nature, the ladies they like this gold so much. And usage of gold. So we can prepare as a coin, and also we are using dental work, plating, reflectors, as well as jewelry. Everything okay, sir? You said when we are entering inside of the jewelry shops, we will be very happy, especially ladies. What about men's? They are always thinking about the price. It is very high, very expensive. Even cannot able to buy in the normal middle class family people. But you are saying that you are working with gold nanoparticles. Are you a rich person? Definitely not. So these questions I know well. I can able to read your mind voice. So all the people have these same questions. I can give an answer for this one. So gold price 1 gram up to date 24 carat 4,960 rupees. But the gold chloride is a powder. That gold chloride HAUCl4. It is also called as a iuric acid. So this one, the 5 grams, it is 55,000. For 1 gram, it is 15,320. So see, 1 gram gold chloride, it is enough. It comes around 15,000 rupees only. So when compared with the other research, so if you are buying antibody, enzymes, if you are buying other chemicals, the cost will come around 15,000 rupees. So therefore, in my concern, the 15,000 is not very expensive. Okay. Then second point, you just look that 1 gram. So we are taking and dissolve into the 80 ml. It will come around 63 molar solutions. So 63 molar 80 ml we can get it from 1 gram of gold salt. That 63 molar we are not going to take as such. We have to dilute it, volumetric dilutions. From there, we are going to take only 1 millimolar solutions. You know well how much level we have to dilute it. Okay. The 80 ml solution is cost 15,000. From there, we are going to take 100 microliters. 100 microliter, that is zero point 0.1 ml. Then that one we are going to dilute again. That will prepare a 10 ml. From that 1 millimolar 10 ml solutions, we are going to take a 0.5 ml only. So if you have that 15,000 rupees of gold chloride 80 ml, then you can able to complete 4 PhD with that chloride solutions. So whichever I take 1 millimolar 0.5 ml, the cost if you calculate all the things, it will not go more than 500 rupees. So your thinking is wrong. Understood? So don't think that the gold chloride is very expensive. It is very cheap cost only, but we are not going to take entire gold chloride. So small amount of gold chloride only we are going to take. But the beginners, those who are newly started their research, I'm advising them, please avoid to use initially the gold chloride because you have to take a training. So start with silver nanoparticles. And when you start to use it, then you will know the success and failure rate and the aggregations as well as stability problem by experience. So after you got the experience, then you can use the gold chloride. So for my students, even a master students, if they are coming, I don't worry about the cost. So I can give to them. But at the beginning for 3 months, 4 months, I ask them to take a training through the copper as well as gold. Sorry, copper and silver. You know, well, cost wise, it is cheap cost. So we can use that materials. After getting the training, I ask them to use the gold chloride. That is the best way. So your thinking is wrong. When you compare the overall cost, it will not go more than 500 rupees. Okay. So gold nanomaterials. Come for the nanotechnology. So the surface coverage is more. It is a bulk materials like a bulk gold, whichever it is. See here, this type of gold, jewelry, golds, this type of things. This is a bulk materials. It is yellow color. But nano gold spherical size particles up to 30 nanometers, it is a wine red color. This bulk gold not soluble in water, but the nano gold is highly soluble in water. This one surface coverage is less. See here, we have a big size of footballs. See, just imagine these colors of the balls is equal to the football size. This much area we have it. Only we can able to cover 6 big size of balls. Take an example where you are sitting that room. So if we are going to fill that room through our basketball or football, we need 100 balls. The same one, if we are filling through the tennis ball, it will come around 50,000 balls. Why the number is increased? Because of smaller size. The size is more means surface coverage is more. Surface coverage is more means their electrical conductivity, physical, chemical properties will be high. So that is the reasons people are looking the nanoparticles, and also the band gap, and also their semiconducting nature. It is important. Okay, we can go very in depthly about the nanomaterials. Many people they have been given a talk about the nanotechnology, but they failed to highlight in few points. So I have seen many people started to do your home mini project with nanoparticles. These points is very very important. So the nanoparticles is in between the molecules and bulk materials. So molecules, take examples our body fluids like a DNA, RNA, it is in the molecular size only. The nanoparticle is middle of bulk and molecules. Okay, the gold nanoparticles or gold nanomaterials are three types: gold nanoparticles, gold nanocluster, and gold nanodots. In this gold nanoparticles case, you can able to see two divisions: spherical particles and plasmonic particles. Spherical particles means spherical size particles. Plasmonic particles, for example, gold nanorod, gold nanoprisms, gold nano triangle, gold nano pentacone, gold nano hexacone. These are all comes under the category of plasmonic nanoparticles. Core cell nanoparticles, dumple shaped nanoparticles, rotten like size nanoparticles, flower like nanoparticles. All are comes under the category of plasmonic nanoparticles. Spherical particles also in the same category it will come. But main one important things, these gold nanoparticles, whether it is fluorescent, no. These gold nanoparticles are not fluorescent because of their surface plasma resonance. What is mean by surface plasma resonance? You know, well, when you take the semiconducting materials, there are two band gaps. One is conduction band and another one is valence band. So when I take a class for our master students, they are having a confusion. Which one come bottom, which one go top? Whether valence band can come bottom or conduction band can go up. So I asked them to do remember simply. So we are in university, so we have a vice chancellor. Vice chancellors generally we can call as a VC. So V first letter, C next letter. So V valence band is the bottom and conduction band C is the top. So it is very simple clue. So you can keep in your mind. So the conduction band is the top, valence band is the bottom. VC. Okay. So what is mean by surface plasma resonance? So all kind of nanoparticles, gold nanoparticles, silver nanoparticles, copper nanoparticles, platinum nanoparticles, palladium nanoparticles. Whatever we are saying as a nanoparticles, their oxidation state should be zero. It is called as a metal nanoparticles. If we take a bulk gold jewelry, their oxidation state also is zero. That is a bulk metals. Similarly, our nano-sized particles also having the oxidation state zero. That is why it is called as a metal nanoparticles. Whichever the material having the oxidation state zero, that materials having surface plasma resonance band. That is simply abbreviated as a SPR. It is very, very important property in the gold nanoparticles, silver nanoparticles, platinum nanoparticles, palladium nanoparticles, copper nanoparticles. Sir, what about plasmonic nanoparticles? Plasmonic nanoparticles also have the surface plasma resonance band because their oxidation state also is zero. Okay, so the definition of SPR, the collective oscillations between the conduction band and metal surface electron is called the surface plasma resonance. So therefore, the metal surface electron is needed. That metal surface electron, it is only applicable for the metal oxidation state zero. One important questions people can ask. So gold nanoparticles oxidation state zero, silver nanoparticles oxidation state zero, but iron whether it is possible to prepare iron oxidation state 0 iron nanoparticles, zinc 0 nanoparticles, or titanium 0 nanoparticles. Yes, it is possible, but it is not stable. It is not stable. Even within a minutes, that iron 0 become a iron 2 plus or iron 3 plus. That is why it is called as a iron oxide nanoparticle. That kind of material is called a metal oxide nanoparticle. So whichever the metal oxide nanoparticles you are seeing, you can easily conclude it their oxidation state it is not 0. It may be 2 plus, 3 plus, like that. So similarly, the titanium dioxide, Ti2 plus, zinc oxide, Zn2 plus O. Then iron oxide, there are two iron oxide, Fe2O3 and Fe3O4. So one 2 oxidation and another one 3 oxidations. So these materials will not be stable for a longer time, immediately get the atmosphere air and it convert to the oxide nanoparticles. So that is why gold, silver, platinum, palladium and copper are highly stable. When compared with the other things, platinum is highly stable. Next one, gold, then silver, copper is least stable. Even 1 week only maximum reported or 10 days reported. After that, it's become a copper oxide nanoparticles. But other nanoparticles, zinc oxide, iron oxide, nickel oxide, titanium dioxide, these are all things easily can produce because it is not stable. Okay, that is why this gold nanoparticle, it is not a fluorescent because it has the surface plasma resonance band. What about the cluster? What about the nanodots? The nanocluster, it is atomic size particles. It's like a cluster. So that one doesn't have a surface plasma resonance band. What about gold nanodots? Gold nanodots, it's a new class of gold nanomaterials. That one also don't have a surface plasma resonance band. But these two things, which one? Gold nanocluster and gold nanodots, these two things having the fluorescence nature. Okay. There are many methods for the synthesis of nanoparticles. These are metal nanoparticles, UV radiation, laser ablation, plasma, and also chemical methods, citrate, Turkiewicz, wet chemical method, chemical reduction method, and sonochemical, sonoelectrochemical methods. These are the synthesis of nanoparticles. Oxidation state 0. See how it is formed. So gold chloride we have taken, this is the ligand, so it is attached. Then we added the reducing agent, it's AU3, it's become a AU0. Because of this reducing agent, it get reduced and it is bind on the surface. So this end is free from the binding, this end it is attached on the surface. So the free ended particles only stabilize the nanoparticles. There are two kind of stabilization, we can see one by one. So this one reduce the nanoparticles, that is why this one is called as a reducing agent. This one capped the nanoparticles, that is why it is called as a capping agents or ligand. Sometimes this ligand can act as a dual role like a capping as well as reducing. Based on the pH, based on the temperature, based on the solvent. See, why we need this surface modification? What will be happen if we are not modify the surface? So these are all the surface modifications, ligands. So you can take a linear chain molecules or heterocyclic molecules or amino acids. But there is no issue, but two things it's very important. One end and another one should be covered with the SH or NH2 or COOH. These are all the ligands. These Mercapto ligands are thiol ligand, amine ligand, these are carboxyl ligand. Sometimes you can keep OH, catechol, OH also you can keep. So these functionalities should be there in both N. Both NSH okay, both NCOH okay, but it should be there SH or NH2 or COOH. So these N can bind on the surface, this N free from the binding. So electrostatic repulsions will come. So these one promote the stability of the nanoparticles and alter the hydrophilicity
and also the coupling with biomolecules, and also the building blocks we can make it, and core cell we can make it. So therefore, whatever nanoparticles you prepare, it may be oxide nanoparticles, titanium dioxide, or zinc oxide, or copper oxide, nickel oxide, or gold nanoparticles, silver nanoparticles, or carbon nanoparticles, carbon cluster, or carbon dot, whatever it may be, ligand is very, very important. Without ligand, you cannot stabilize your nanoparticles. So ligand is very, very important for all kind of nanoparticles. If you are talking about the nanoparticles, you should talk about the ligand. So the selection of ligand is very important. These are all ligands soluble in water. If you want to prepare the organic nanoparticles, you can take an organic solvent and appropriate ligand. You can prepare the organic nanoparticles. So then the amphiphilic nature ligand, you can take it like a CTAP, something you can take and you can prepare. So ligand selection is very important. And in this platform, I want to register one thing, sir. Last class, you said that we can take neem leaves extract. So what chemicals are there in neem leaves extract? You know well, actinoids, flavonoids, terpenoids, carbohydrate, chlorophyll, many compounds are there. That all compounds will act as a ligand. That is why whichever nanoparticles you have prepared from the natural product or waste material, that is still stable. Hope you understand the situation. Next, go. There are two types of stabilization. For any kind of nanoparticle, these two type of stabilization only is applicable. Even carbon dots, graphene quantum dots, graphene oxide, zinc oxide nanoparticle, titanium dioxide, gold, silver, whatever it may be, polymeric nanoparticles, whatever it may be, these two kind of stabilization only is applicable. The number one stabilization is electrostatic stabilization. The next one, steric stabilization. The steric stabilization is exclusively applicable if you are taking polymeric compound. Like a polymer or surfactants, if you take this steric stabilization, it is. See, these are linear molecules. So this SH, it is bind on the surface. And this end is free from the binding. So take an example of one ball. The S is bind. It is a three-dimensional view. And the outer surface COOH. Don't think that it will come 1 kilometer length. If you calculate the length of this compound, it is come less than nanometer. Armstrong structure only will be there. Very small particles. Okay. So therefore, the nanoparticles big size, ligand is small size. For pictorial view, they written like this. Don't think that these linear molecules will come for 1 kilometer length. Don't think that is. If you calculate the chain, it will come only Armstrong structure or near to nanometer. Less than that nanometer. I mean 4 nanometer, 3 nanometer. But particle size 30 nanometer, 50 nanometer, or 20 nanometer. So big particles and the top, the small ligand is attached. Okay, there are many mechanisms involved here. I'm talking about the electrostatic stabilization. So the number one mechanisms are two ends are there. One is SH, one COOH. You are not asking, so that is why I am telling the answer and question both. I am asking by myself, and I can give an answer for that one. Which one you have a more chance to bind? So according to hard acid, hard base, Lewis acid base concept, hope you have studied in your first year as well as bachelor degree. That one hard acid, hard base, soft acid, soft base, HSAB principle. So according to that principle, this gold, silver, copper, whichever it is there in oxidation state 0, that all act as a soft acid. But this SH, it is acted as a soft base. So without having any force, it is attached on the surface, it form a mono layer, single layer, mono layer, unique mono layer. Within a fraction of second, it will form. So that is why SH having the preference to bind on the surface. If we don't have a SH other end, say if we have a NH2 instead of SH, if we have NH2, what will be happen? So NH2 only will bind. The NH2 mechanism, it is a free radical mechanism. That mechanism is called as a Michael-like addition mechanism. Okay, both end COOH. So definitely the one end will bind. And also there is a chance to tilt again like a bending of one, like a U shape. So inverted U shapes, how it will bind, the both end can bind. But here there is a more chance because of the lengthy. So COOH, it will be free. The COOH means that is the electrostatic attractions, it will bind. So if SH is there, different mechanism. NH2 is there, different mechanism. COOH is there, different mechanism. OH is there, different mechanism. So don't get a confusion. It is only applicable for metal nanoparticles. But metal oxide nanoparticle, it will be different. If oxide layer is there, means oxide like a silane or other mercaptopropionic acid silane, that one different mechanism. Oxide bond can bind. OH bond bind. I am talking only about the metal nanoparticles. So this COO minus will be free from the binding in a solution. So that one is the negative charge. So here negatively charged, here negative charge, negative repulsive force will be there. This is called the electrostatic repulsive. So if you see these values, it is the instrument name is called particle size analyzer. If you give your solution, you can able to measure the surface charge. The surface charge will come in the volt, millivolt, minus 20 millivolt, minus 30 millivolt, plus 30 millivolt. It means that surface charge. And there are some rules and regulations. If the surface charge is more than 25 plus or minus 25 millivolt, the particles are highly stable. If nearly 50, more stable. Very rare to go for more than 50. If lesser than 20 millivolt, the particle is going to get aggregation. Therefore, you have to do the surface modification. So we have to take a stabilizing agents or ligand appropriately, and you should stabilize the nanoparticles. Sir, if we are taking we prepare the nanoparticles without adding ligand, whether it will be stable, it will not stable even 1 hour. If we check their zeta potential, it will come less than 20 millivolt only. That is why it got easily aggregations. Okay, polymeric compound, what will be happen? Take an example of one football or a tennis or one basketball. You are coating one thick layer on the outer surface. Then if you are touching two balls, the outside core only can touch. The inner core cannot be touched because the very thick layer is there in the outside surface. This type of stabilization is applicable only for polymeric material. This stabilization is called steric stabilization. So whenever you are working in the nanotechnology, these two concepts should be very clear. Then only you can able to publish the article, you can able to submit your thesis. Okay. Applications of gold nanoparticles. There are many applications. Biological, imaging, drug delivery, cancer treatment, then diagnosis assay, radiotherapy, etc. we can do. Gold nanoparticle is it fluorescent? As I discussed earlier, these two only is a fluorescence. Let's see about the gold nanocluster. So gold nanocluster is sub-nanometer size. Size should be 1 to 2 nanometer only. But spherical size particles higher than 10 nanometers. That one having the surface plasma resonance band. This cluster doesn't have this one. This is the cluster, 1 atom, 2 atom, 3 atoms. So this is the atomic structure. So many numbers of atom combined together, it produces like a cluster size. See here, one cell, 13 atom, 55 atom, 147 atoms, 561, 1450, like that cell can produce. So that one is called as a cluster, but it is in the 2 nanometer size, 1 to 2 nanometer size. The synthesis, as I mentioned earlier, this is the bottom up approach. This is the top down method. So you can do both way and you can prepare. There are many things. This is the best paper. This G et al. Published in the 2009 using bovine serum albumin as a capping agent. This is a protein simply mixed with gold chloride and bovine serum albumin, incubate 2 minutes, and after that sodium hydroxide added 12 hours they incubated and stirred at 38-degree temperature at dark room condition. The next day they got the red fluorescence. The drawback of this one, this BSA, it is very expensive. It is a protein and need to have a dark room condition, 12 hours heating, and the temperature is for 40 degrees. So if you are failed to do these conditions, you cannot prepare. This is the main drawback of this nanocluster. There are many particles people are reported. This blue one, BSA, this is antibody, another one antibody red fluorescence, and this one is pink color fluorescence lysosome. The many kind of fluorescence people have been developed. But among the different one, WIPGR, red fluorescence is highly valuable one. Why, sir? So red fluorescence people are using for bioimaging application, theranostics applications. For example, the traffic signals, the red color you can able to see, there is the indication of stop. Why, sir? Why don't we keep green as a stop signal? Not only India, in global level, that is the signal. Green is ready, go. Then red is the stop. Why, sir? We can able to see long distance. Similarly, it is applied for sensor LED many applications. But this red emissions, why it is important? For especially in a cancer therapy, I work in cancer therapy. So bioimaging people can use this red fluorescence material, especially these nanoparticles are highly stable. If they are using dyes or other inorganic nanomaterials like a cadmium, telluride, or other materials, it's a toxic. But this gold, you know, well, people are using for medicinal applications from ancient days. So that is why it is novel. What is the specialty for this red fluorescence? The specialty is it will not harmful to the cells. If you are taking blue color emissions, the absorption can come in the UV radiations, with GR, indigo, UV radiations. If you are passing the UV laser, it is harmful to the cells and it will destroy the cells. Visible light, long time exposure, again, is the problem. But laser, it is called near infrared light, NIR, near infrared lights. So that is the red lights. So that one, it can easily penetrate into the cells and it will not destroy the normal cells. Particularly, it can kill the cancer cells. In last class, I forgot, you hope you do remember, I mentioned the differentiation between the normal cells and cancer cells. The cancer cells pH 5 and it will not be able to stable even if we are giving 40-degree temperature. Normal cells can stable live up to 55 or 60, then pH 7.2. So similarly, we can pass the laser inside, we can produce the heat inside, then accordingly we can kill the cancer cells. It is called the thermal therapy, photothermal therapy. Okay, the best example I can tell you, hope you have seen these days, if you go for hospital for back pain complaint, the doctor can give advice to take a IR radiation massage. There is one lamp, double layer, triple layer classes will be there. Then big wire connections will be there. Then they will ask us to switch on the lamp and put the back side of your backbones. Then radiations will go inside and you can get good relief. Doctor giving the advice to take the IR radiation massage for the back pain. The reason is the IR radiation, I mean red light, can deeply penetrate inside of the cells. So because of these reasons, red emission is very important. So therefore, drawback of gold nano cluster, long time and needed a very expensive chemicals as a ligand and complicated procedure. Only few reports available for a red emissions. Especially this fluorescence. See here, this bioimaging. It's cover the cancer cells. This it's a red color. We can able to see this one. We have prepared nano cluster from our lab. See here how much red this color. Okay. Demerits of this one already I discussed. Dark room conditions, ligand very expensive, lengthy procedure, difficult to handle the ligand because people are taking DNA to reaction time 12 hours, 37-degree needed to heat it. Then gold nanodot, it's a new class of fluorescent gold materials. It is an intermediate between the gold nanoparticles and gold nanocluster. So gold nanodot, intermediate of gold nanoparticle nanocluster, no surface plasma resonance, 1 to 4 nanometer size. So it doesn't have a SPR band, but it is an intermediate of nanoparticles and nanocluster. The nanocluster, as I mentioned, small atoms combined together. But here, see here, this is the spherical particles. The inside core is AU0, but outside complex, AU1 complex is produced. So because of the ratio of AU0 and AU1, the gold nanodots fluorescence can appear. So we have published this much paper with this gold nanodots. Only few people are working in India, this one. In abroad, Taiwan, HT Chang National Taiwan University, and many people are using working in this area. And biosensor bioelectrochemistry editor Albert Mercosi from Spain, he is also working in this area. Only few people are working. We are also working in this area. So it is similarly applied for several applications: bioimaging, detections, and sensor, light emitting diode, solar cell, supercapacitor, many applications. And come for their general application sensor. One more class we can discuss these things well details because I have to discuss little more, but I can explain this one, endosulfone. Hope you remember that 1 hour talk, whichever I sent to you, audio, there I discuss about this endosulfone. So this picture we have taken from Kasargod village from Kerala. So see here birth defect, this cattle only have 3 legs, and see here this birth defect, still they have a birth defect because of the endosulfone. Endosulfone they just use for the cashew nut, and their water source is lack and slowly bioaccumulated, and it is not able to recover. Still now they have a birth defect. And the melamine is a food contaminations. So in the year 2018 in China and 2008 in China and 2005 in United States, almost few lakhs pet animals were died because of this food contaminations. So this melamine, it's a white powder. This white powder highly soluble in water. So illegal manufacturers of milk product like infant, well, these days many milk product is available. But I checked with our Indian product, they doesn't have this type of contaminations. They just illegally ordered this one. The melamine structure, if you see, just like a benzene ring and 135 position NH2 and 246 inside of a ring nitrogens. So 6 nitrogens groups are there. Well, according to our quality control from Tamil Nadu government as well as Indian government, they have one method to analyze the proteins. That is method is called hazardous method. So it is based on the nitrogen. So if they are mixing this powder inside of the milk and milk powder, it will give a thickness, highly dense milk you can get it. But you cannot able to distinguish these materials from milk. That much dense you can get. When they are taking the reading of protein, it will enhance the protein reading. For example, they have only 5 liters of milk. They ordered 15 liters of water and 1 gram or 2 grams of this powder. If they are mixing, then it will show like this 15 and 5, 20, 20 liters of milk. How much quantity is needed, that much quantity it will show the protein quantity. But when it is go inside of our body, it will produce the insoluble solids, that is cyanuric acid. That cyanuric acid will mix with our urine, uric acid. It produces an insoluble solid, that is a kidney stone. So because of the formation of kidney stones, the 2 years, almost 3 lakhs, 4 lakhs of pet animal as well as small infants were died. After these incidents, a lot of research papers came as a outcome. And this is the mercury. This one is a very big history. There is a one place in Japan. That place is called Minamata. So small, well, Japan is an island. So this city is near to the sea, but there is one mercury industry. They are illegally dispose the mercury contaminated water inside of the sea. Then through fish, it is bioaccumulated. In that city, their major food is fish. Then through fish, they just inhale the mercury. Then immediately they got severe health issues. Then many people were died and also birth defect obtained. After that, they investigated and they found that because of this mercury, this metal mercury, from there the disease name is called Minamata disease. So these are all things very important. And also these days some chemicals like anions, sulfides, cyanides also toxic. Well, acid rain, the major responsible one is for the H2S. It's become a HCl and H2SO4. These photographs taken in Czech Republic. So still see here this right side photographs, Czech Republic, acid rain, the victim of acid rain.
நம்ம
And
அப்பா
see
வந்து
here,
சந்தேகப்பட்டு வேற யாருன்னா அந்த மாதிரி வந்து திருடிட்டு போயிருக்க போறாங்க.
admin, please mute the mic of that person.
அப்பா
Thank you. So therefore, the anion sensor is very important. This cyanide also is very important. I can go a little faster. Then result output from our lab. I can discuss today a little bit research oriented things. The left side, this is the chemical. This chemical name is called thiocyanuric acid. 3 and 135 SH and middle of the ring nitrogen. If you are dissolving these substances, it shows the green fluorescence. I just simply mix gold chloride inside, then it's become a red. I was surprised. This type of unexpected result is called as a serendipitous. The name is called serendipitous. Unexpected result, like X-rays. It is unexpected investigation. This is called serendipitous. After that, I ordered cyanide, and then again I got the green fluorescence. Then I found that there is some decomposition in these nano dots. So this paper we have published in nanotechnology, now impact factor 3.87. See, this is a structure of that ligand, UV visible, and 506 is the green emission. See here, this is the green emission. It's a daylight colorless solution. Okay. And the synthesis is very simple synthesis. Please be remember, I just shown the synthesis of gold nanocluster. How simple this one. Water I taken, then ligand I added, then gold chloride I taken, then polyethylene glycol for surfactant. Without having polyethylene glycols also we have prepared sodium hydroxide and we produce. The entire overall reactions, how long it take, less than 5 minutes, exactly 8 minutes. At room temperatures we have prepared. As I mentioned earlier, this one shows red emission. The red emission is very rare to prepare. Many applications are there. So they have to wait for 12 hours, 24 hours, dark room condition, very expensive chemicals. But with small molecules at room temperature, we have been prepared these nano dots. And also, fortunately, it shows the red emission. See here, 622. This is the particle size. Particle size has been calculated to be 3 nanometers. This image, everything done by myself only. Even transmission electron microscope when I was Portugal, I just imaged by myself. Very interesting. And it's stable for 1.5 months. And pH effect, it is stable and high intensity obtained for 12 and 13. And it is highly stable up to 1.5 months. Then quantum yield we have calculated. These are the already reported one. Our value is higher than that one, almost 5-fold or 10-fold higher than the reported one we got it. The novelty, don't need a proteins, other things, room temperature, and also water soluble, and the red emissions obtained, benefit for the bioimaging and photothermal therapy applications, and 2 to 3 order magnitude higher quantum yield we got it. And I applied for cyanide sensor. I ordered cyanide, then the peak fluorescence was quenched, and this is the intensity. Then based on this one, we have calculated the detection limit is 150 nanomolar. This is the lowest value from the reported papers. So our one is the lowest value, somewhat novelty. Then 18 times lower value than which was recommended by World Health Organization. 2.7 micromolar they have reported, but ours 18 times lower value also we can able to detect. Then in the presence of other ions, see here, these are all the nitrate, phosphate, sulfate, acetate, all are red color, but when I add cyanide, that one only it is the colorless. And as I mentioned earlier, we have to look very carefully all the things. Even don't think that the UV visible spectrum is just only for the characterization. We cannot get very high information from UV visible. So we can get it. See here, we got the mechanism from this UV visible. See, I ordered this one. This is the original peak, and slowly new peak, 2 3 peaks appeared. Then after that I compared with this one. This one it is for the nanoparticles in the presence of cyanide. Then this one is the TCA ligand, this peak. So these 3 peaks retained there. It means that decomposition has been appeared. So because of the decomposition, again green fluorescence reverted. So again we got the green fluorescence. So we got the clear mechanism from this UV visible spectrum. Don't think that UV visible spectrum not very much important. If you are looking very carefully, sometimes it will help you to predict the mechanism. We predicted. So this is the mechanism. So these are nanoparticles. Then green color is the ligand, and this polyethylene glycol. Then after adding cyanide, AU cyanide complex is produced. Then PEC and TCA is liberated. This TCA is green color. Again, they revert back to the green color. Then we confirm with mass spectrum. So these are all the peak for AU cyanide, and this is the ligand peaks. And we use for a tape water, lake water, sea water as the real sample analysis. We got good recovery. Then second one work we have been published in ACS Applied Materials and Interfaces 9.22. Actually, in this paper, previous paper, I just bought the DCA, this DCA commercially from Sigma Aldrich. But this ACS paper, I have been synthesized the ligand by myself. See here, this is the one compound, chemical compound. Then I added formaldehyde and sodium hydroxide. This adduct is produced. Finally, this compound is produced. This compound name is called 6-mercaptotriazole and tetracycline. So here see 4 and 6, 6N is there and SH. Very strong fluorescent compound. This one doesn't have a fluorescence, but this is a ligand. So then I ordered simply gold chloride and sodium hydroxide. Again, surprisingly, we got red fluorescent, the same room temperature condition. And see here, different excitation, and this one high emission. So therefore, we have fixed 360 nanometer as an excitation wavelength. This is the 3D views. That is why we have to show somewhat different way. That is why our paper went up to 10 impact factor. So see here, well, clear pictorial view we can see. This one it is higher, this one excitation, this one fluorescent, this is the emission wavelength. So we done using very simple free software only. And these are particle size, again it is a 2 nanometer, this is the red emissions we have time. The particle size see here, it is around 3 nanometer. And it is also stable for 3 months. And this XPS peak, as I mentioned earlier, this is the AU0 and AU1. The middle core, central core AU0, then outer core AU1. AU1 will not be as a AU1. It is a complex. AUS, it's a complex. So how much AU1 is there, that much fluorescence you can get it. For here, 60% we got it. So high fluorescence we got it here. Then this isopistic point we obtain. This one we use cyanide. Here, this one shown high cyanide selectivity. Then fluorescence also decrease when I add cyanide. Again, Au2S here is produced, and we taken Raman spectrum. This is the conformation spectrum of Au2S, and the particle size increase. This is also because of Au2S, and mass spectrum we taken, that is Au2S is confirmed. Then is the Steinwalmer equation, and this is the diameters. This one is the dynamic light scattering values. So using these are all things we have predicted the mechanism. Then very importantly, the interferences in the presence of anions and cations. So interestingly, when we add this sulfide, that time only it is produced colorless compound. Then all the elegons, I ordered all the things. See here, mixed ions, all the ions. Still it's shown the red fluorescence. But when I add cyanide, again fluorescence was constant. Then very importantly, we have prepared paper-based sensor. This is the paper. This one is the Wattman paper. In this Wattman paper, wax we coated. This is a wax printed Wattman paper. So this one centimeter diameter. The distance also 1 centimeter. This is a wax-free area. After we prepare this one, instead of ink, we have to fill the wax. So that is the different printer. That printer name is called wax printer. Then we take a print out using our normal Wattman 1 size paper, then heated using the hot plate for 180-degree, wax melted. Then this area, wax area, this is the wax free area. The reason to take a wax, this is a hydrophobic area, this is a hydrophilic area. We can able to hold the materials here because it is a liquid. So we added the nanoparticle all the area. This is the blank, we didn't add anything. Then increasing concentration of sulfide we added. This is the color of Au2S. Then see here the fluorescence slowly quenching. Then finally it is disappeared. Then this one we just use by microplate reader, and this one we publish in that paper. And recently my student Mardupandi has been published one articles in Journal of Hazardous Material. The impact factor now is 10.5. After I joined here, we have been published. There we developed the smartphone aided paper based kit for on-site monitoring of material. Using smartphone, we have developed the kit for on-site monitoring. This one is the basic fundamental. Okay, so I can come for the conclusions. So I have discussed about gold and gold nanoparticles, nanocluster, and as well as nanodots, and our research output I have elaborately discussed. And I have to acknowledge my PhD research scholar Chandru, Mardupandi, Mercy, and Goglishwaran, Lalit Negi, and my master students last year Abhilash, Kunashegaran, Ramya, Ibrahim, Nishat, and Afridi. And these are all my collaborators from Malaysia, then Fernandez Hercules, Spain, Ely, Sweden, then Michael, Portugal. So I got this wax printed paper from him only. And Corolla, Germany, and Portugal collaborators, Begone Espina, Juan, Carlos, Manol, and Martha Prado, and BSA Crescent collaborator, Professor S. Kutirani, and D. Sumati, and Nashir. These are all my publications. We have published articles in cover articles also, very high impact factor. Even we have a impact factor 12, 10, like this, 5, 6 articles, and the average impact factor is 4. The total publication is 35, and this work highlighted in Nature India. Finally, I had to thank for your kind attention. I'm very sorry I just almost take a 40 minutes time extra, but I hope that you all have been enjoyed my talk. So now I have to check the questions. Yes. Gold nanoparticles are toxic or non-toxic. So everything is toxic if the level is exceed or higher level. So we cannot say even food, even biryani also is toxic if you are keep on taking the green. Means, so therefore, if certain level there is no toxic. If you exceed that level, definitely it is toxic. Applications of gold nanoparticles, there are many. Already I discussed. What is the importance of zero oxidation state gold nanoparticles? So zero oxidation state, if it is there, then only it is a stable. That is metal nanoparticles. If it is not zero oxidations, it's still ions. Gold chloride Au3 plus their ionic oxidation state. Au3 plus, it should be reduced by using reducing agents. There are many reducing agents. I forgot to mention strong reducing agents, weak reducing agents. Strong reducing agent, sodium borohydride, hydrazines, lithium aluminum hydride. Weak reducing agents, our citric acid, ascorbic acid, these are all weak reducing agents. So if you are using weak reducing agents, you can get a big size of particles. If you are using strong reducing agent, you can get smaller size particles. And also the speed, addition speed. If slow additions, you can get the big size of particles. If fast addition, you can get the smaller size of particles. It will come based on your experience only. So therefore, the oxidation from 3 plus to 0, it should be converted by the reducing agent. Sometimes your ligand can act as a dual role. Like your tannic acid, gallic acid, the catechol group is there. Itself, it will reduce and it will bind on the surface. This binding nature, instant synthesis only. When you are taking gold chloride, that time you have to add ligand, then reducing agents. Will not take a time. Overall reaction I mentioned there only 10 minutes. Then our paper, one paper we haven't published, that is 1 minute synthesis. See here. Is it possible to synthesis within a minute nanoparticles? We are the examples. So this paper we haven't published. Journal of Hazardous Materials. See the title. 1 minute synthesis of, see here, 1 minute synthesis of green fluorescence copper nanobody. Yes, the world is going very fast. So within a minute we have prepared. See, my name and my student's name is there, Crescent University. We publish. Okay, everything is possible. So within a minute it will bind on the surface. That much faster. Aggregations can keep on because of the T stabilization. It's a very interesting one. I want to register here. We are not working majorly when we are conducting the BTech or UG or PG laboratory classes, because our laboratory is the top of the UG and PG laboratory, nanotechnology laboratory. So these people, when they are using hydrochloric acid, when they are using hydrogen sulfide, the vapor can come up. Because of that vapor, we put our nanoparticle inside of the refrigerator. Even we didn't open, then inside means we put in the conical flask and closed lid also there, but the particles got aggregations. That much sensitive. So therefore, we have to keep very nicely inside, and you have to use the alumina foil as well as parafilm. You have to cover all the things. Accordingly, you have to safeguard it. If some outside, some air or some toxic vapors can come out, then it will be getting aggregations. And also my student said that the instrumentation laboratory is another one building. When he is coming, with nanoparticles, it's a 3-floor. He has to come through the lift as well as step. So during that time, he shaked the nanoparticles, then got aggregations. So gold that much sensitive. So therefore, whenever you go for TEM imagings, whenever go for characterization, whenever you want to transfer to one peaker to another peaker, you have to look the environment surrounding. Even if you don't have electricity, if we on the generator for a electricity source, it produces some gases, you know well. Because of that cases also particles can get aggregations. So if you ask with my students, they can tell one day story about these things. So that much sensitive nanoparticles. So you have to take care of this one. We cannot able to learn at one day. It is based on the experience only we can able to learn these things. Yes, it is possible to use for the diagnostics applications. When I was in Portugal, when I was in Taiwan, I worked in this area. It is possible. For SARS-CoV-19, yes, the research is going on, but not yet completed. So hopefully it will come very good result. Disadvantages, yes, there is a disadvantages. That is why you don't use without. I mean, don't use with your free hand. You have to use the gloves. You have to use the other protective things. Then it is okay. But inhalations, very rare chance to inhale. Even if it is go through our sweating spore other things, it is very trace quantity to remember. So 1 gram 68 molar, then we have to dilute to the 1.1 ml. Then further we are taking the 0.5 ml. So therefore concentration is too much low. So therefore you don't need to worry about that much toxicity when compared with cadmium and other things. The particles behave differently in nanoscale. Yes, as I mentioned earlier, these particles, it is in yellow color. Which one? 2 nanometer, 3 nanometer cluster, as well as nanodots. But spherical particles, 10 nanometer to 30 nanometer, is wine red color. Then beyond the 30 nanometer, 60, 70, it's a little bit pink color. Then plasmonic nanoparticles, sometimes it's blue color, purple color, different colors. So based on the shape and size, it will be varied. And I hope that I have answered for all the questions. So thank you so much. I hope that you have enjoyed a lot. Now I request Nivedita to deliver a vote of thanks.
Thank you so much, sir, for your wonderful presentation. We students from Crescent know how much busy you are. From morning to evening, you have classes to take. After that, you coordinate this internship program. Even after the completion of the session, each day you communicate with the students to resolve their queries. You are always engaged in various kind of activities, sir. From your very busy schedule, you prepared and delivered this great presentation. Coming to your presentation, you started with the basics of gold nanoparticles and explained why silver, gold, and platinum nanoparticles are stable over other oxide kind of nanoparticles and the differences among gold nanoparticles, nanoclusters, and nanodots. You explained the various synthesis of gold nanodots and the importance of ligand selection, surface modification, etc. Then you detailedly explained the synthesis, characterization, and application of TCA modified gold nanodots in cyanide detection. Thanks for elaborately explaining the details, sir. To the world, you may be just a teacher, but to your students, you are an idol, an inspiration, and you are a family. Appreciation can make a day, even change a life. Appreciation goes a long way as a motivator. In that way, you never fail to appreciate us, sir, and recognize our resources. Thank you so much, sir, for being our motivation. You're definitely a person we all look up to. And I'm very sure your journey in the field of nanotechnology will be blossoming forever. I once again express my gratitude to you, sir, on behalf of everyone. I also thank the participants from my heart. Thank you all. Thank you for the session, sir.
Thank you so much, Nivedita, for your vote of thanks and nice comparing. Dear participants, for your information, I want to tell one thing. Actually, don't look where you are. Place is not a matter. The matter is how you are doing work. If you are doing hard work, definitely one day you can able to achieve it. See, we are not a very big university. At the same time, we are not very small university. It's the middle. I mean, the facility wise as well as the area wise, we are middle. But with this available facility, we went up to the impact factor 10.5. Already I shown you. Then quantity wise, quality wise, we are number one in our department. So everything is possible. if you are doing hard work. So please do hard work. And also don't worry about the place. So your idea, if it is good things, definitely it will go. So with this small university, people are thinking that only big institute and foreign country people only can able to publish this much level. Definitely not. If your idea and if your written format and if way of presentation, if it is good, definitely they can accept it. As Nivedita told earlier, I'm also editor one journals. I know well. So we are not looking the country, we are not looking about the place. We are only looking the quality and the genuinity of the data. So after seeing the data, we will easily know about how much hard work you done for one data. So if you look my data, all baselines is very good and the curve is very good, three-dimensional view and the thickness, including the arrangements of the figures. So we have concentrated that much level. That is also main secret to went for this much impact factor. So your supervisor only have to train for these things. So as well as based on your experience, you can learn the things. Whenever you read the articles, you have to look these much things. Don't look only the concept. Also, you can check the quality of the figures. You always have to read the high impact factor journals. Then only you will know about the real novel work as well as new ideas. So thank you so much for your kind attention. Feedback link already posted in your WhatsApp as well as YouTube charting links. So please fill it within 30 minutes. And tomorrow, day after tomorrow, we don't have any sessions, but any important points if I want to convey to you. So please check your WhatsApp message. I have a plan to send a few messages. So please read it that messages. See you by Monday. Thank you so much. Have a nice weekend. Admin, please close the session after few minutes.
Okay, sir.